네, 마이크를 테스트하고 있습니다. 번역 마이크를 테스트하고 있습니다. 번역 마이크 테스트 중 하나, 둘, 셋, 하나, 둘, 셋. 번역 마이크를 테스트하고 있습니다. 번역 마이크를 테스트하고 있습니다. 마이크 테스트 하나, 둘, 셋, 하나, 둘, 셋. 번역 마이크 테스트 중 잘 됩니다.
testing. So this is track A. The topic is large language models and agentic AI. It's going to be started in a minute. Please make your way to sit. Yeah. And also, please make sure your phone is in silent mode. Yeah. Okay, good afternoon, everyone. My name is Jungseul from POSTECH. It's my honor to serve as the chair of Track A. And welcome to Track A on large language models and agentic AI. Today, we are pleased to welcome leading researchers and industry experts who will share their latest research and insights into the evolving landscape of large language models and agentic AI. I hope today's session will provide valuable insights and inspire meaningful discussion. Please note that this session is being live streamed on official YouTube channels of Global AI Frontier Symposiums. Yeah. Now, let me begin with our first presentation, a keynote given by Woohyung Lim, the head of LG AI Research. He's going to deliver a presentation titled "The Future of AI Industry." Please give him a big applause of applause. Yeah. Ah.
Hello, everyone. I'm Woohyung Lim, the head of LJI Research. It's a true honor to share this meaningful stage with so many experts gathered here. Thank you for having me. As this symposium's name suggests, we now stand at the very frontier of AI. In just a few years, AI has begun to reshape from the ground up how we work, how we research, and how we make decisions. And the pace of that change accelerates year after year. Today, I'd like to share two things with you. One is where the technology trend toward agentic AI is headed. The other is how that shift is actually showing up as changes on the industrial floor. I want to trace both together, the sweeping current and the concrete ground where it lands. First, a quick look at where we stand. For the past few years, we've marveled at how generative AI like ChatGPT or Gemini writes text and creates images. On Gartner's hype cycle, generative AI has passed the peak of inflated expectations, and as the hype settles, it is finding its place in real, practical use. And the keyword that has taken the button and climbed to the top of the curve is agentic AI. So in 2026, AI has moved past generating sentences into the era of the agent, one that reasons, plans, and acts on its own. Let me set the one line that runs through everything today. The essence of agentic AI is that it collapses the cost of cognition. The complex analysis and deep judgment that once took a handful of specialists a great deal of time, AI now performs. When that cost falls, the entire industrial order built on top of it is redrawn. Agentic AI collapses the cost of cognition, and that collapse reorganizes the industrial ecosystem. There is today's one line. This became possible as three technical leaps converged. Reasoning that breaks a problem into steps, plans, and self-checks. Tool use that gives the model hands in the real world through search and code. And the orchestration of specialized agents cooperating on complex tasks. As this lock together, AI crosses from a tool that answers to an agent that works. Yeah. This shift is already reshaping capital markets and society at large. A prime example is Anthropic's roughly $1.5 billion joint venture with Wall Street firms like Blackstone, Goldman Sachs, Hellman and Friedman, and others. What matters is that this is not a standard investment. That enormous services and consulting market is exactly what AI, now that the cost of cognition has fallen, is beginning to observe. As agentic AI integrates deeply into core enterprise workflows, routine tasks disappear and human experts move up to directing the entire system. Oh, let's quick look at the video. Maybe you see in this video. This year, the keyword physical AI came up again and again. In the past, physical AI mostly meant demo level showcases, robots running and jumping. This video means something different. Humanoids autonomously process nearly 250,000 packages over 200 continuous hours, live streamed for the entire run. It was a controlled environmental trial, but the point is clear. The real question for physical AI is not how impressive, but how well does it actually do the work. And this was the first public proof that a robot can do real work reliably and well over a long stretch of time. Physical AI is not a distant future. It is a present already crossing the threshold. Now, let me walk you through the diverse challenges we at LG are actively driving inside this great reorganization. First, a quick introduction. LG AI Research, established in December 2020, is LG Group's AI think tank, leading our AX initiatives and pursuing research to make the world better with AI. Let me say one thing up front. The reason LG has become good at AI is that we have kept taking on the challenge of solving real industrial problems. Across electronics, chemicals, displays, and telecom, we grow our models by trying again and again to solve the real problems we met on the floor with AI. On the foundation, we are steadily building AI leadership along three axes, developing our own proprietary foundation models, building expert AI deployed directly into real industrial settings, and advancing trustworthy AI. In our 5 years, we have aimed not at research that stops at papers and benchmarks, but at research that leads to real customer value. We develop frontier models ourselves, apply them across the group's real operations, and feed what we learn back into research a virtuous cycle. Through programs like the LG AI Graduate School and LG Amers, we also cultivate the AI talent of the future. Technology, people, and the field, carrying these three together is how LGI research works. The name EXA1 stands for Expert AI for Everyone. The name carries our aim to put expert level AI in the hands not of a few but of everyone. And building on the know-how and capability, we've accumulated developing EXA1 in-house. We are creating AI models of world-class caliber. In the same line, in the model we are building through Korea's government-supported proprietary foundation model program is KXR1. By internalizing core technologies, mixture of expert-based hybrid attention, an upgraded tokenizer, and more, KXR1 aims to be an efficient model that delivers better performance at lower cost. Beyond that, KXR1 does not stop at the domestic stage. It aims to be a global frontier model, and we are advancing its performance further even now. We aren't doing this alone. We developed KXR1 together with a consortium. LGA Research leads model development, Superb AI handles data building, and on the infrastructure side, we partner with Furious AI and Friendly AI to scale and deploy the model widely. We also work with partners like Hancom, EastSoft, LGCNS to figure out how it can make a real impact in everyday life. XR1 is our own model, lightweight yet built to deliver top-tier performance. In version 4.5, we developed our own vision encoder from scratch and added multimodal capability, so the model can deeply understand documents and handle question and answer across multiple files at once. In particular, it can now read and understand documents containing complex charts, tables, and diagrams, and act on the content to carry out real work. On the strength of these capabilities, XR1 is already doing real work across a range of business tasks, reading and summarizing reports, interpreting data, and handling repetitive document work, lifting productivity on the ground. Let me share a bit more of our research. For example, we are developing industrial anomaly detection systems that help on-site experts and handle real-world challenges like processing unseen data the model never met during training. In particular, the AI detects anomalies that are hard for people to judge and flag them on its own, so the necessary actions can be taken on site in advance. As a result, it significantly reduces the costs that would otherwise be incurred when an accident occurs. In short, we dig deep into methodologies that take foundational research and apply it directly on the factory floor. At LGAI Research, we carry out this breadth of AI research aimed at genuinely solving real field challenges at a world-class level. According to the recent Stanford AI Index report, XR1 was named a notable AI model, and 4 of the 8 models representing Korea are from our own XR1 series. This shows XR1 is not a local player, but a world-class competitor on the global stage. Building on XR1, LG is constructing an AI ecosystem across industries, from manufacturing and R&D to bio and public B2B sectors. For example, we built an enterprise AI agent, ChatXR1, on top of web search, coding, and document creation. We strengthened reasoning and deep research. It searches internal knowledge and documents to produce grounded answers, and even for complex multi-step requests, it plans and executes on its own. Beyond simply answering questions, it drafts reports, organizes scattered material, and takes over repetitive work, delivering reliable, purpose-fit results and sharply lifting productivity. It's now used by over 80,000 employees across LG Group every day. We've moved past the stage where the agent merely assists. Now, the agent performs the work and people set the direction. Another example, an AI that optimizes raw material supply scheduling in petrochemicals. The agent autonomously optimizes the entire flow from naphtha intake to cracking and generates schedules that adapt to rapidly changing conditions. A task once handled strictly by human experts is now driven by the AI agent, delivering significantly higher profit than ever before. In particular, the optimized scheduling the AI produces raises production efficiency, translating directly into maximized business profit. Complex industrial problems we assumed only humans could solve are now being solved by the agent on its own. In finance, we built Exxon Business Intelligence for market and demand forecasting. It's an advanced corporate analysis system in which a specialized AI agent, acting as economist, analyst, decision maker, and journalist, collaborate autonomously, handling the entire process from macroeconomic analysis and risk assessment to decision support and final reporting. In fact, within LG Group, we have steadily advanced AI forecasting market demanding and predicting raw material prices. Bringing those forecasting technologies together, we are now taking on the larger arena of finance. By having many agents analyze and understand vast volumes of data, we predict a company's future outlook with even greater accuracy. Notably, in partnership with the London Stock Exchange Group, we validate this capability against the global financial markets, proof that a Korean model is working at the very center of world finance, detecting risks in fast-moving markets ahead of time and raising the reliability of financial decisions. For data governance and legal risk management, we built the AI agent based in Exxon Nexus. It autonomously tracks the full life cycle of the training data sets used in a model, comprehensively analyzing legal risks such as copyright and privacy. What's key is that the AI agent analyzes the legal risk tied to the data in fine detail on its own and carries this out meticulously even within complex multi-stage data structures. By assessing risk factors at every step, from collection to use, it lets organizations build the safest, most trustworthy AI models. If trust is the foundation from within, sovereignty is the foundation facing outward. When the cost of the cognition collapses, who performs the cognition, where and at what cost becomes the competitive edge itself. Yet, when you train an outside model on your data, decades of hard-won floor know-how can flow out along with it. Depending entirely on someone else's intelligence is convenient in the short run, but can be the most expensive choice in the long run. That is why we build our own foundation model, XR1, and seek to control efficient inference with our own hands. Having our own AI capability without being locked into others' ecosystem, there is technological sovereignty, and together with trust, it is one of the two foundations for placing agents at the very heart of the industry. In biomedicine, we are driving innovation with Exome Path, a model specialized for pathology. Yeah. Let's take a look at some short video. In hospitals, doctors rely heavily on microscopic pathology images for initial diagnosis. Exome Path analyzes these complex tissue images alongside genetic information to help predict diseases. Beyond that, it also makes it possible to design patient recruitment for clinical trials with far greater precision. And in the end, it acts as a powerful AI assistant that helps clinicians diagnose faster and far more accurately. Now let's talk about the way we work. So far, we've seen that XR1 and its agents can do, but the real change happens in how we weave these tools into our work. With AI now inside industry, how will the factory, the lab, and the office change? What shifts on our floor, and how should we work alongside AI? Let me look at this through three scenes: the changing factory, the changing R&D, and the changing organization and people. First, the lights off factory, the dark factory. Here, the entire plant from production to quality control can run fully unmanned with AI self-designing and operating the whole process. Even today, factories already read vast streams of data in real time and adjust themselves. At the physical AI we saw earlier, and equipment senses anomalies and responses on its own, robots read their surroundings and carry on the work, and processes find their own optimum to push yield together higher. Yeah. In the near future, we will see fully autonomous factories operated together by agentic AI and physical AI. AI will carry out the manufacturing work itself, inspect quality on its own, and even improve yield. performing this entire process autonomously without human intervention. Rather than guarding the plant through the night, people move to designing and supervising so the system runs correctly. This is not a distant fantasy. It is a change already becoming reality in part. And when that happens, location strategy changes too. Where companies once built factories chasing cheap labor, they will now choose sites by entirely new criteria, such as where energy is to secure. Second is the transformation of R&D and the industrial landscape. In problems with too many possibilities for humans to exhaust, new drugs for intractable diseases, new materials, AI produces genuinely new methodologies. Where research once relied on human intuition and long experience experiments, AI now searches vast hypotheses, spaces quickly, screens promising candidates through simulation, and compresses the experiment and learning cycle itself. A search that took months shrinks to days, and combinations no one thought to try get examined too. For instance, we are researching models that analyze disease mechanisms and predict a therapeutic response. This shift is spreading beyond drugs and materials into demanding fields like energy and manufacturing process. And as the speed and the very method of research change, entirely new business domains that didn't exist before will be created. Lastly, this will drive fundamental change in our organizations and how we work. Reshaping the workforce to match these shifts is essential. Conventional administrative and repetitive roles will be absorbed into AI agent systems, and specialized domains will either disappear or newly emerge. And as the volume of work AI performs alongside human growth and its scope widens, we will need to rethink the very space and the ways in which AI and humans work together. So we must move beyond simply adopting technology and proactively prepare for sweeping change across our organizational structures and security governance. And this change ultimately returns to a question about people. When repetitive, standardized tasks are absorbed by agents, human work does not disappear, it moved up. Just as the engineer who wrote code becomes an orchestrator who designs systems, people shift to roles demanding higher judgment and creativity. The catch is that this shift does not happen by itself. Without the chance to learn new skills, the speed of change becomes a gap. So reskilling and talent development are not optional. They are essential. That is why we invest in programs like the LJR Graduate School and AMS. Building the technology matters, but so does cultivate the people who will work alongside it. Our mission, a world where everyone realizes their dreams through AI, also means no one should be left behind by the pace of innovation. So, what is our role in the age of AI agents? In enterprise management, humans must evolve from being mere operators into three roles. Why must we evolve this way? Because once AI takes over much of the execution, human value shifts from executing more and faster to deciding what to do and why and taking responsibility for the outcome. Execution can be delegated, direction and accountability cannot. So the human role does not disappear, it is redefined upward. First, the approver, the one who owns the final risk. However, precisely AI analyzes and executes the decision to accept those results and be accountable for them belongs to a human, especially for irreversible or high-stakes matters. The authority for the final call must stay in human hands. Second, the supervisor, the one who orchestrates the process. In an environment where many agents work at once, the human designs and monitors the flow so the agents collaborate in the right direction, stepping into correct course when something goes wrong. People become conductors who make the work run rather than doing every task themselves. The third, designer, the one who architects the business itself, which problem to solve, what value to create, and how to structure the systems and workflows toward the goal. This is the highest, most creative role of all. In the end, the future is not about humans stepping aside. It is about human AI joint decision making, where our responsibility and AI's capability succeed together. The next key agenda is building an agentic ecosystem. To build a true agentic ecosystem, three elements must be examined together. The first to review is the central brain. Core models, we must check whether foundation models can serve as the foundation, solving complex problems through autonomous reasoning. And the second is the specialized agent. Whether powered by the brain, agents can independently execute complex workflows across finance, legal, manufacturing, and more. The third is a physical integration, where the agents can bridge into the physical environment and infrastructure to transform real-world productivity. Brain, expertise, and physical connection, only when all three are in place and converge does a true agentic ecosystem come to life. And one thing is clear. No single company can complete this ecosystem alone. It turns only when those who hold the core models, the experts who know the domain deeply, those who build the chips and infrastructure, and the companies that apply it on the floor all connect. The KXON consortium I mentioned is exactly such an attempt. LG AI Research leads the models, while many partners take on data, infrastructure, and deployment. An ecosystem, too, grows from connections that share a single direction. That is why I want to stress openness and standards. For agents to talk to one another, connect safely, and produce results we can trust, we need common rules. In conclusion, now that the cost of cognition is collapsing and the industrial order is being redrawn, the AI race is escalating into an all-out nation effort. It is time to establish policies and frameworks that integrate all three perspectives: national, corporate, and individual. At the national level, we urgently need a strategy to counter big tech's AI ecosystem monopoly and safeguard technological sovereignty. At the corporate level, it's it's no longer about merely adopting technology. companies must secure true AI transformation competitiveness that transforms the business model itself. And ultimately, at the individual level, we must build a social safety net that ensures AI inclusivity, so no one is left behind in this transition. The future is clear. AI will accelerate execution, but defining its direction remains the work of human beings. When we define that direction well, our true AI leadership will be complete. Thank you for your attention.
Thank you for the insight. We have Q&A session. Yeah. So I think we have time to take a question, one or two. If you have any question, can you please raise your hands so that our staff will give. 여기 마이크 좀 전달해 주시겠어요? 여기 파란 셔츠.
Thank you for your presentation. I would like to ask about the EXA1's development plan. In terms of the parameter size, LG EXA1 has 236 billion and 33 billion two model in Hugging Face, open rate side. Compared to Chinese model, GLM, Minmax, Kimi, Mistral, yeah, there are a lot of models over 700 billion parameter size. So, which means that the performance of LLM is lower than Chinese model. So, what is the plan of LG and what is the opinion of the that kind of the difference in parameter size?
Yeah. KXM version 1.0 is has a 236 billion billion size parameter size, but we actually enlarge the model parameter size. But I think that only parameter size doesn't the only factor of the performance. But anyway, we are enlarging the model parameter size. Yeah, actually, yeah. Maybe not open today, but yeah, okay. Continue to enlarge.
Okay. Any other questions? Yes, please.
Thank you for your presentation.
Thank you.
How are you managing your token budgets? What kind of strategies are you implementing to make sure that you get the performance that you want, but without breaking the bank?
Actually, LGR Research is somewhat small company, so we allow to use people to some other solutions, AI solutions. Not manage much for now, but I think we have to do it shortly. Yeah.
Yeah. I think we have some time for one more question, one last question.
Thank you for the insight. You mentioned trust and sovereignty as the reason for EXA1 being developed internally using internal data sets rather than opening it up to use outside data sets. What was the trade-off of using internal data only as opposed to using outside data for your training purposes?
Yeah, thank you for your question. it is very difficult decision, but I think the company's competitiveness is bound to AI model in the future. So uh, building the model is a very difficult thing, but we are trying to build better model to uh, enhance our company's competitiveness. Yeah, but anyway, using our other companies' AI solution, commodity solutions is very efficient, I think, but it's some choice of as the company how to build the company's competitiveness. So yeah, and case by case, I think.
Okay, thank you for your
Thank you.
insightful keynotes and Q&A session. And please give them warm rounds of applause.
Thank you very much.
From now on, we will have panel discussion. Panelists, can you come to front? It's going to be starting in like 3 minutes. Yeah. Okay, now let us begin the panel discussion. So we have diverse background. I mean, we have panelists from diverse backgrounds. And first, we have Aaron Kubil, professor at University de Montreal, and Younghyun Chung, who is CEO of Korka, and Dong-Ah Lee, professor at Yonsei University, and Juneun Choi, applied AI architects at Entropy. Please welcome them with big rounds of applause. So to begin with, I want to start with somewhat easy question. So I want to ask where we are right now. So can you share your most interesting or valuable application that you see of about application? I mean, of LLM or AI agents. So
Sorry, you want us to talk about like work
so
we've
your
done, or
the most interesting or valuable application of LLM and AI agents in your experience?
okay? I guess let's see. How I would I? It seems to me that one of the things that's interesting about this technology, and this has been true of the very early days in deep learning, which is essentially where I did many years of my work, is that this is a horizontal, right? This is a technology that goes across many, many different domains. So from what I do and the kind of work that I do is much more on the fundamental side. And so I guess one of the things I think is remarkable about this technology is just how many domains it touches. And if you make insights or breakthroughs in that are linked to one particular domain, those go over into other kinds of domains pretty much instantly. So I think there's a lot to be said for that and for the power of this kind of technology to sort of do sweeping transformations across the board. In terms of actual areas that I'm interested in, I guess, like I said, I'm much more on the sort of fundamental side, but one of the areas that I think is really exciting, and this is something Noam Brown mentioned this morning, is on the multi-agent side. So this isn't really an application domain because, again, I think multi-agents can be applied across a wide range of different application areas, but I think that's a really, really interesting problem domain that I'm most excited about right now.
I'd like to mention about our product because you asked about the most interesting applications because we are building interesting applications. Yesterday evening, I have a seminar with early childhood education conference. 한국말로 육아교육 학회였습니다. I have no idea about early childhood education, but our product, I ask our agents to make a literature review recent 3 years, and that agent autonomously found recent researchers and then make a wiki style literature reviews. As a graduate student decades ago, I did days and weeks for making that part, but our agents can make that literature review. So I'd like to mention about that. If we use AI good and we have a good results, and then as a human, we can just focus on what we have to do as researchers or workers. And our product is in the viewing area in the booth. You can check the Kraken.
Okay. I want to definitely say that the very good application of large language models and an AI agent will be automating my routine and doing my tedious job instead of me. So writing an email, writing a first draft of my report, and evaluating my student because I'm working as a professor in university. And one more information about me is that since last year, I have run a small AI startup, and our startup has worked with the big manufacturing company. So we are trying to building an AI systems that can automate the workflow of that manufacturing company. So they asked us to building such system or AI model that can automate their typical workflow and their job. So that will be the very benefit of using the large language models.
Hi, my name is Junan Choi from Anthropic. Please consider that my answer could be like, if you join the industry side, it's gonna be helpful. But I left the school over 10 years ago, so my delivery could not be helpful for you at this point. But some of you already know that around 2 weeks ago, a Korea Anthropic office is launched. So I got hundreds of emails at a day. So I'm trying to do like answer a lot of to answer as much as possible, but it's hard to answer. But so I try to make an agent to read the customer's email and then try to find the answer to deliver it. But the important thing is that I don't want to collect the data from the website. I only want to collect the data inside of our database or other tools. So in that case, I need to make an agent that get the information only inside of my tool. And then I also need the information from the outside. So I need to make a two agent and then combine and then compare by themselves and then try to get the fancy answer to the customer they really need. So that kind of things, like Professor told. So that's the point I'm very interested in nowadays.
Thanks for sharing all the interesting application in your life and in your job. And as a second question, despite all the interesting applications and nice service based on AI, we know they have limitations, right? Can you share your thoughts about what is the most challenging or most important challenge to make AI better or LLM better?
Okay. I think it's better to start from me because I'm gonna get the lowest level. So the challenge is that so nowadays, thanks to professors and researchers, so we can get like frontier models. But when I got a lot of chance to do the POC with other companies, so we can do the POC very well, and then we can get the very successful result. But uh, when they go to their C levels, the C level always ask me like, how can we get this answer? What the process steps? Do you know the reason? So in that case, sometimes we got very hard time to answer this, and then a lot of time we fail to put this in their production. So I think the trust or like auditability, explainability could be the biggest challenge at this time.
Yeah, I totally with this opinion, and I want to add some comment. Yeah, I also think that the biggest challenge or limitation of the current AI system is not about the capability. So the verification is more becomes more bottleneck for deploying the AI system into the real world problems, because these days AI can really works well and can do various of things, but they cannot check their output or their result. So coding task will be a good example, because these days I really have worked with the AI agent to implement something for my project. So I asked something to AI agent, then the AI agent can write a lot of code and the tens or hundreds or thousands of the lines of code, but I'm not sure whether this code works well, there's no error or some broken part. So I have to ask, oh, did you do it well? Then the cloud code says that, yeah, it will show yes. But after then, I find the error and the broken part. Then I ask again, why did you say, yeah, you did it right? And at that time, the AI just said, oh, sorry, I think I missed it. So that's the most problematic part of the AI agent systems. They cannot reliably check their output or verify their answers. And this problem is connected to the POC problem. Yeah, many companies are really working well for their POC project, but it does not usually go to the real use case, because somebody asks the question, who should be responsible if this goes wrong? So the verification I think the verification is the major bottleneck, and this should be addressed soon for better deployment.
I think my answer will be similar to Mr. Che. As a OpenAI partner, only startup in Korea, I can be your partner, Anthropic. Please contact me after this session. I think because as an OpenAI service partner, we provide solutions and applications to enterprise level, industry or companies and lab. I think the main limitation is not just model capability or technology or applications, but the difficulty of controlling where the information or sensitive information is allowed to flow in real organization settings. I think the bottleneck for us and maybe everybody is the deployable control, not just intelligence.
Yeah, I think I agree with all of the statements I've said before. I'll just add, again, kind of underlying what I was saying earlier, that this is a technology that can be applied in many different domains, and depending upon the particular domain that you're talking about, the bottlenecks or limitations might be different. For example, in applications to healthcare, I'd make the case that maybe one of the major limitations there is actually access to data. That's something, whereas in other domains, that's not really our problem. If you want to apply AI to, say, government processes and make government more efficient, it's not really necessarily a data limitation there. It's going to be much more along the legal and ethical frameworks, and maybe even resistance by organized labor that you could imagine that would be the limitation or bottleneck to seeing that kind of system deployed. So I think once we get into the specifics of a particular domain, the limitations or bottlenecks could be a bit different.
Okay. Thanks for all the interesting, insightful responses. But verification is indeed a bottleneck and challenging. But at the same time, as the earlier keynotes mentioned, verification is kind of one very promising role of a human being in the future AI industry, right? So I don't know whether we can really bypass all the verifications and data collection and so on, but I think they are technical hurdle that we need to address. So in this sense, there are a lot of approaches to improve the performance, accuracy or computation efficiency and so on, right? So can you share your own vision on how to address the challenges in developing LLMs and AI agents? Vision, just your vision, and maybe someone try to build new architecture of LLM rather than just transformer, and someone tries to, I don't know, build.
So what is the major limitation that we would want to where we want to see breakthrough? Is that the question, or what?
In my understanding, one common limitation that we share is verification or accuracy, I think.
How do we fix that? Is that the question?
Yeah. Or maybe you think there can be some other limitations, right? Data sets. So maybe you try to address this problem in your own way, right? So maybe you can share how you do that.
Sure. Let's see. I guess it seems to me that in cases where I'll deal with or comment on the verification problem. So in some cases, verification is relatively easy. Cases like coding, or at least in limited areas of coding, it can be relatively easy. You can write unit tests and you can get this kind of verification cleared. In other cases, verification becomes the bottleneck problem in the sense that it's not at all obvious if in cases where it's not a quantitative problem, where maybe you want to write a nice poem. How do you verify that? These are all pretty interesting problems. How we get around that is an interesting question. I don't actually know a great answer for that, so I don't have an answer for you there. I think, well, one thing I guess I could say is that ultimately, this is probably one of these fundamental problems that we sort of make progress at little by little, right? We get, for example, we can get models that are able to judge the quality of a poem or something like that, and we can just kind of refine them. We can get, if we are able to use multiple agents, we can get committees of agents and ask them. And so I think this is maybe an approach to solving those kinds of problems, if we talk specifically about the verification problem. But yeah, it's a very, very hard problem in general. I don't know.
Okay, so you ask about the vision, and I'd like to change the word vision to dream. And the keyword may be AI for science and the transformers. You may know the 2017, the Attention is All You Need papers. After that, current, all of the models are based on transformers. And the other side, people says AI can help science or research. So personally, I'm using our product and I'm testing with our product that whether AI can help real research autonomously. So whenever I found interesting papers or interesting ideas to make new LLM or new AI models, then I sent these articles and thoughts into our product, Kraken. So I'm sending everything into the workspace that calls Beyond Transformers, by the way. So at that workspace, I'm gathering all of the information, interesting ideas into that. So our agents, science agents, is running 24 hours to think about new approaches. And then it gives me new test ideas using GPUs to test. So that approach is our approach about overcome the current limitation of the foundation models. That's our research. So maybe I hope we can show our results recent near future.
Yeah, that's a very good point. And from a few months ago, there are a few hot keywords that are getting attention in academic and industry, which are harness engineering and loop engineering, you know. So harness is everything around the model. So the tools that AI can use, or the way the AI can verify their steps, and the way they check their outputs. And I think so as I mentioned, the verifiability is the major bottleneck. So the harness engineering or the harness itself can be a good promising direction to solve those challenges. Because in the harness or the loop engineering, we can design the framework or the system that enforce the agent to iterate their process to achieve the goal. So in that process, the agent take an action and review their previous steps and take another actions until it success the succeeding tasks. So designing a good harness will be a good solution for resolving the solution. And if there are two different companies having the same model, they will get totally different results. This difference does not come from the model itself. It comes from the harness. So the effectiveness and the reliability of the harness will be the key factor to achieve the higher quality result or the better outcomes that we expect to the AI agent system.
Yeah, I totally agree with Dr. Lee. So whenever we have a new model, so for example, this week we got the Sonnet 5. So in this case, we guided the customers to change all the harness, all the prompt, everything. If we change it just a little bit, because we don't know, because when model trained and then we can when we can do model, everything could be changed. So, but customers got really hard time suffer from changing any their architecture system to evaluate and then the result, because their service is on the production. It's very sensitive to change something. So I'm not sure it is a vision or not, but the industry need to set their own architecture or a system to change prompt or change harness or test the harness and then check their result. I know it's hard to make a golden data set to check the result, but nowadays with the researchers, I wish we can focus on to have a kind of criteria to have the score result. That's my opinion.
Yeah, I also suffer from that issue 1 month before when Anthropic released the new version of but so we had to change all the harness and some prompt.
I will let you know my phone number, so please don't. Yeah.
Thank you.
I actually just want to follow up. As an academic, I'm kind of curious. what do you think are the sort of scientific questions around the harness? Because from a certain point of view, you know, there's the model and there's very specific components, but then the harness is kind of like the part you put it in to make a product out of it, and then you go. So it's interesting to think about the harness as being sort of something for an academic to study, and I'm kind of curious if you thought about what kinds of questions you can ask specifically about the kind of harness you have, and does that make sense to focus on that as a topic?
Yeah, the agent committee that you mentioned also can be one example of the harness. And recently, I have reviewed some papers about the idea discovery for the paper agentic paper writing. And in that paper, they tried to find the very promising idea by using the MCTS algorithm or constructing the framework or environment to evaluate how this idea is good enough or the promising in the future. So all such practice will be categorized into the harness engineering, I think.
Thanks.
Great. So we need to do some research about harness engineering, right? So at the same time, I mean, so we have very plenty of time, right? So maybe you can ask questions to each other, and it would be really a great discussion, right? So, but since this track is about LLM and AI agents, so we somehow presume that AI agents is based on LLM. Do you think this assumption is valid, or do we need to think another architecture of AI agents? So can you give your thoughts about this? Maybe.
Um, frankly, I don't know. So I wish it's not. We keep our architectures a little bit longer, but yeah, but I'm pretty sure is that we change a lot of things a day. So, for example, if you check the security harness from our side, is we already changed a lot inside of our company. So, I'm not sure if we change all the architecture or not, but the 100% sure is even every model, every checkpoint, every other model, the harness should be changed a lot, and then the result could be changed changed a lot. That's my the opinion I can share.
So in some sense, I mean, so one follow-up question is that actually, in my understanding, LLM model is trained by unsupervised learning, essentially, fill the blanks and so on. But there is no notion of AI agents harness or something. So maybe at the same time of building AI harness, maybe we need to somehow figure out how to train new LLM or some other model for agents. Is there any efforts?
I think not the training itself for the harness. We still check the harness and the results by ourselves manually. So I think you already know some of the services for the financial service, like our financial service. That the reason we provide that kind of a particular service that so we just check the input data and then check the output data, and then we try to set the evaluation system, but still need to check the manual check. So we cannot check all the result, but at least the sampling, and then we have to check every day, every week, and so on. So yeah, that's my.
Actually, I'm working on some other projects. At there, we somehow figure out that just we need to co-evolve not only the agentic harness but also the model, so that you know, given harness model X some pattern, but in the end, when we try to new type of harness, the model cannot understand this behavior at sometimes. And maybe co-evolution of model and harness may help the improving our performance and so on. So
Yeah,
maybe
I think that's the reason we need to make a harness every day, every time. So I think people got different personality. So like the model. So the model also can get their like a different like a characteristic. So I think that's the reason that we have to change the harness. So I know we all have a hard time to migrate from the previous model to new model, and then previous harness to the new harness. But I think we have to be familiar with this environment. So we the professors and researchers can give us like a new fancy model. I want to use that model. I I have to be familiar with this environment. That's my opinion. Yeah.
great.
In my opinion, I think the AI agents will be based on LLM, current LLM, because LLM is so powerful. But it will be, based on the current LLM, maybe 10 years or 1 years, or even 1 month, because AI is so fast. And you mentioned that current LLM has a very obvious limitations, but people are work around that limitations, such as skills, MCPs, connecting informations, and more harness and agentic engineering. So people are using current LLM even if it has limitations. So because the current LLM is so powerful, so I think agents will be based on the current LLMs. And we can make each agent, maybe Claude agents and Codex agents and any other agents can talk about to solve the problems and do tasks each other. So maybe it can be years, but maybe 1 month. But I think current LLM is so powerful. That's my opinion.
Yeah, right. So I do agree with language is really good representation method and
Yeah, because the chair asks about the architecture breakthrough of the LLM, so I want to add something. Yeah, I'm aware that there have been a lot of attempts to make a breakthrough for the architecture of the core engine beyond the transformer. So like a Mamba or the latent reasoning model, and there are a lot of attempts. And yeah, such architecture should be able to capture very long context with significant efficiency. Yeah, that would be very beneficial. But similar to other opinion, the harness also important with the development of the core engine or large language model as well. So I hope that some researcher have developed some very innovative architecture of the large language models.
Okay. Yeah. So my take on this is that I think we agree that for the foreseeable future, whether we're talking 1 month or 5 years or 10 years, that LLMs are probably going to be the core of these agents. From my point of view, for a few different good reasons. One of these reasons is just that this is the technology that everybody's lining up behind right now, and a lot of investment is going into making that technology efficient. And so it's essentially kind of building its own moat for why it's going to be very difficult for another technology, say diffusion models or whatever, to sort of replace them, because there's just a lot of efficiencies that have been built into LLMs. And so I have a former student, Sarah Hooker, who wrote a really nice paper on the hardware lottery, is roughly the title of the paper. And this is the basic idea that once you have, in that case, they were talking about GPUs, and that, like, neural nets basically go really well with GPUs, and so that's what sort of promotes the use of a particular kind of neural net. We're sort of building our own kind of, not exactly a hardware lottery, but sort of an infrastructure lottery around these LLMs. And it's going to be pretty difficult for another technology to come in. It's not impossible, but it's just very difficult. The other thing that LLMs give us is a reasoning capability that's kind of unique to them. And maybe it'd be easier to do it in another way, or at least possible. But this is presented as a fairly natural thing for these models. And what this reasoning does, and I really want to emphasize this, is it allows us to sort of decompose problems into smaller problems and allows us to generalize better. This is like a really powerful technology that these models are just capable of doing it relatively easily compared to maybe other kinds of paradigms. And so when we talk about generalization to kind of newer tasks, something a little bit different than what you've really trained on, that ability to generalize led by this kind of reasoning or chain of thought, I think is really, really important. So another technology that can replace LLMs is going to have to be able to replace those kinds of properties.
Yeah, right. I mean, language that enable us to have reasoning ability. I truly agree with that. But in some sense, LLM is trained by only text in some sense. But if we want LLM replace human beings' labor, it should mimic how human being is trained, right? So we learn something from not only text, but also image, video, and also at the same time, we walk around, move around, and learn something, right? So in this sense, maybe for next generation, I don't know if we have this, but the new agents should based on at least VLM or at least VLA or some other multi-input, multi-output model, I think. So I don't know. We will see in future, but yeah.
So I mean, like current models, there's, I mean, I think Anthropic would be, actually, you guys don't do very much multimodal stuff, but there's kind of different ways of approaching this. One way is, and maybe this is going to be ultimately the way that wins, is it's just a unification of all of these different modalities, but through a kind of a tokenization and then treated within the same model. I'm not really up on sort of the latest of that. Most of that work is sort of in industry and behind closed doors. But that is certainly a way that one could imagine going, is that you introduce early in the pre-training process, not just text data, but also sort of in the pre-training process, I should say, not just text data, but video data and image data and that other kinds of modalities early on, and they're able to reason and this kind of chain of thought reasoning, not just in text tokens, but in these other kinds of tokens as well. That's a possible future that I could imagine.
I think that this topic is covered by other sessions, physical AI or world models. Well, in my opinion, current LLM is based on the text because it's approachable and relatively inexpensive data. And so that's why we're building this. So physical AI field, the data and data generations and data labeling is expensive than text, just crawling or whatever. So I think many people want to have a world model. So that will bring researchers to or companies build a world model using multimodal. So I think that's the money issue, I think.
Yeah, I totally agree with all the opinions. And from ancient, human tried to encode very highly dense semantics and meanings into the lexical tokens, words, and language. So language provides very good medium that other modality can be easily merged and fusioned. But I also believe that there is room where the language cannot cover in the semantic space. So that's where the VLA and word model should cover in later. But yeah, large language model provides very good initial point to provide the intelligence.
Yeah, when I was in school, there is only like a text embedding model. But nowadays, I can find that the multimodal embedding models. So I was surprised that the text like a Super Mario, the image can be found. So I think this kind of the things can happen in the large language model too. So it could be like a picture or other format, but that definitely could be possible in the future and maybe soon. Yeah. But I'm not sure about the Anthropic society now. But anyway, yeah, I believe that.
So maybe we talked about presences, right? But if we think about after LLM or after AI agents, we cannot avoid physical AI or robots. But other than that, well, perhaps you may know some other next things after AI agents. And can you share your idea about what comes next after AI agents? Maybe, or we all agree with next item is physical AI.
Many people say quantum.
You mean like quantum AI?
No, I don't know. Quantum physics, I think. Quantum computing.
But just having like I guess I was assuming we were talking about like next next sort of AI technology, I guess. Or I mean, well, I guess I can. So on the physical AI side, maybe this isn't necessarily a big category of what's next, but one thing I guess I could say is that when this is an instance of physical AI, but when it comes to something like autonomous vehicles, right? So these are I think this qualifies as physical AI, but it's not usually what people think about when they talk about sort of robotics. But I think it very much is a case of that. But one of the things that's been interesting, and I think it's an instructive example for us, is that autonomous vehicles have been relatively slow to deploy, right? So unless you're living in San Francisco or a few other places like that, you're not going to probably see a lot of autonomous vehicles on your streets. Well, I'm from Montreal, and it's going to be, I think, a long time before we see in the snow autonomous vehicles there. It's a much more complicated environment, and I actually think that one of the reasons for that is because of there's the sort of clean, clear examples that are close to what these data sets these models are trained on, and then there's sort of the other cases, right? So if we think about, we were mentioning human cognition, right? We have like system one thinking and system two thinking, and one of them is much more reactive. And most AI is that kind of system one reactive kind of thing. It's stimulus response, right? Input, output. System two is truly a case where it's sort of your much more cognitive load. You're like thinking about the problem. It's a much more sort of conscious effort kind of thing, at least for humans. Well, LLMs with chain of thought actually give us that kind of capability. So to actually use those kinds of models they, I think, offer us the capability of maybe allowing these models to generalize more and be able to be deployed in scenarios that are much more, let's say, unstructured. So I actually think that that's not a what's next necessarily, but that actually gives us a sense of how this technology could help push physical AI forward.
I don't know. It's the big next thing in AI, but I think the most important thing in AI is the information flow control. Without that, the world will be disastrous. The cybersecurity issues, maybe Anthropic knows better, but the foundation model AI is so powerful now. So if we lose control, then it will be disastrous. So I think information control is really, really important right now. So not sure this is a big next thing, but it is very important.
Speaking of flow control, and then also we talked about verification. So as a researcher, we report a bunch of benchmark scores. At there, we typically saw like 80%, 60%. But in some sense, as a human being, well-educated human being, that score must be 90 or 99 or something, right? So are we at the stage where we say it is enough, or how far should we go? Like 90% is enough, or should we looking for some easy application where we don't care much about the accuracy? So I don't know, but so when I try to find some new projects or new research topic, I mean, to be honest, it is somewhat hard to say to students whether we should push accuracy from 90 to 99, or maybe we solve much more difficult problems where the current state of the art is only 10% accuracy, and we're looking for something, some breakthrough from 10 to 30 or something. So I don't know which one is better, and I just want to ask. how you
Oh,
think of it.
yeah. Frankly, I'd like to say that it's just my personal opinion. It's too much enough, because I satisfied that even previous our Opus model, because the models are better than me. I cannot do something. I don't know a lot of things than the model. But as we said at the very beginning of this talk, so trust, security, or like a control is really, really important. I would like you to focus on this area, because, for example, one of my favorite companies is Samsung Electronics. They, in the semiconductor area, there are a lot of like steps. I also know that like there is a etch, a photo, like this kind of things complex, and then repeated, and there are hundreds of steps. In this case, we cannot know the how process going well, or the middle step. So the Samsung Electronics customers sometimes can curious, my chip, where is my chip, or how can I see the process during during the making of process. But it's hard to show them. It's hard to get the visibility. The other them got the similar like issue. So in my case, I try to see the process, like you said, the chain of thought. I always try to type, show all the thinking process, but still hard to understand all their or their decisions. So every day when I make the AI agent, I try to see all the log. Why did you call this tool? Why did you decline this tool? Why did you stop the while loop? So, but it's sometimes it's hard to understand. But at this point, I believe that there is something that the reason the model stopped, but I don't know yet. So I try to find the reason. So I think we still need that like the transparency from the model itself. Yeah.
I agree that I think current AI model is already far beyond human intelligence-wise. So, but as you mentioned about the accuracy, workflow-wise, even if each step is 99% accuracy, correct, the 10% or the 10 steps, agent's workflow has only about 90% succeeding rate. So if you are asking 99% accuracy, it's a one turn. It's a multi-turn or workflow-wise. If 99%, 1% failure for 10 steps already make 10% failure. So it is not just a one-turn task. A human being, or we, or workers, or researchers, we are doing a very complex task. So 99% should be means a whole task. So we are maybe people and Anthropic and model makers, and also agents makers are focusing about that.
Yeah, right. Yeah, but my question is, do we need to improve that accuracy in academia, because at some point, a certain point, AI improve themselves by themselves. So I'm not sure which area that the academic researcher can do. And another question to the Anthropic is that, so you mentioned that the practical issues around deploying the AI is really important, but is it the area of the academic or the technical advancement of the AI, or the engineering or human-computer interactions, or?
Mm, yeah. In my case, I need to meet a lot of customer in different industry, but I think that LLM is better than me, but it's still, it's not, it's a, the industry expert is better than the LLM, because the LLM does not have like enough like the particular specific information about detailed like department. So uh, I'd like to ask you to have like a different the expert, like expert large language model for each industry. Is is it okay? Yeah. Is it possible? Right.
And I also hope that the Anthropic are really into the mechanistic interpretability and the constitutional AI. So can I ask some opinions about that? Topics? That topics will be the next frontier of the AI, or the unsolved area in the AI research.
Yeah. That's the most important thing in from the Anthropic. So constitutional AI. So we um we always try to give the society like a beneficial thing. So but and then give the like a right answer without the hallucination, and then with right like any other. I mean, I'm sorry, it's hard questions. So with the constitutional AI, so we believe that we can give the right answer that is really helpful for the human. So we also try hard to focus a lot of time to the constitutional AI. So yeah, that could be the good good side to research.
Okay. So maybe now we can take questions from audience. So if you have, please raise your hand so that our staff finds you to bring microphone. I think it is really rare chance to ask some question to Anthropic and industry and professors. So yeah. Any questions that you want to raise? No.
I prefer questions. You can ask, you can use the Korean. I mean, like, don't hesitate to ask something.
Yeah.
Yes, please.
Before asking my question, I would like to thank you for the insightful speech. And I'm just a typical undergraduate student who currently debating between like getting a job after graduate and attend to a graduate school. When I ask seniors or graduate school students, like many of them recommend either getting a job right away or pursuing the PhD. However, like I personally believe that ordering to pursue like graduate school, I I feel like I think I should get a call from the academia, but I never felt that emotion. So have you ever felt that emotion? Like, could you tell me about it?
Oh, can I say first? Because I was not able to get the doctoral degree. Frankly I failed. I still regret, because during my study time, master's degree, it was a really great time for me because I learned a lot of things. I think that not only for the research, my topic thing, I was able to know how to find the topic, how to discuss with the professors, and then I think that I learned a lot of things from that time. So I'd like to I'd want to say that I'm still regret that I was not able to finish my degree. Professors can give you the right answer.
So from very biased viewpoint, yeah, in the era of AI, the master degree and doctor degree themselves does not matter any longer. But in the graduate school, you can spend a lot of time of finding out the proper research question and how you can solve that challenge or problem, and all such experience will be the good source for you being a good engineer in the industry as well. So, and especially in AI industry, such experience is really important for being a good engineer. So I guess both options are good as well. But yeah, if you want to get some capability of researching about something, then I'd like to recommend you to get a degree. So what do you think about it?
I'd like to answer half serious and half joke. If economic crisis comes, management, finance, marketing graduates go to MBA because no jobs and very bad cycle. So this is the time, I think, as a joke, have very, very fast pace. So if you want to build something or make a company or do something very good, it's very competitive. And the technologies develop so fast. So maybe you can go to graduate school and escape from the storm.
That's not the direction I thought you'd go there, actually. I thought you were going to say now's the time to go out in industry. So from my perspective, so I guess I've talked to many students over the years on this question. From what I can see, it seems very difficult to go from industry back to academia. You get used to a certain lifestyle, a certain amount of income that you won't necessarily have. So that can be a difficult transition. That would be up for you to decide whether that's something you'd be interested in. I could also say that I'm not entirely sure I agree that a degree doesn't matter at all yet. I think we're still at a point where, having a PhD or even a master's opens certain doors that not having one, it just makes it more difficult. It's not impossible. You can still get employed at these great places, but it does make it more difficult, and it makes it more difficult for you to transition. And there are certain doors that are just not going to be open to you, like becoming a professor yourself, if you're interested ever in that. But I will say that, I wouldn't recommend, especially for masters, I think it's a little bit different, but for a PhD, I would not recommend it unless you really felt like you really wanted to dedicate the time to do it. Because I guarantee you there will be moments that you hate your project, you hate the PhD, you want out. That's very common for people to feel that way at some point. Because it's a lot of freedom, but it's also, sometimes that freedom can be a little bit daunting in terms of finding a project and things like that. So yeah, I think you need to decide for yourself whether you have that hunger to sort of launch into that kind of a thing. And yeah, I'll leave it there.
I'd like to add to your answers and my previous answers, because I mentioned that my answer was like half joke, because you can go either way. Academia or industry is good, but this AI world is so competitive and fast-paced. If you start a company, it's good, but you have to expect failure, 99% failure. If you have very good technologies and great applications, but a day after or month after, Anthropic makes something, and Anthropic or OpenAI kills your company, So this is the real world. So if you can go through that, you can start make a company, found a company, or participate in the startup companies. Otherwise, you can just hide from the storm. The 2-3 years, this hectic will be over, I think.
I think either way, this is not a field for the faint of heart.
Great. Any other questions?
I'd like to ask about the future of autoregressive models. Do you think the colony transformers will remain the dominant architecture for LLMs, or do you expect a fundamentally different paradigm to emerge? For example, in robotics, diffusion-based models are becoming increasingly popular. Could something similar happen in language models?
I guess I think I said some things earlier that I think relate to this. So I think if I was to bet one way or the other, I think for the foreseeable future, I do think language models will be these kind of autoregressive transformer models. They have certain advantages over things like diffusion models. Say, for example, the chain of thought style reasoning, right? That's a lot harder to do in the context of diffusion models. It's not impossible, people have done it, but for example, just being able to decompose tasks and to think, like, for example, you need to sort of have a certain fixed amount of thinking time for a diffusion model, right? Just the flexibility on the amount of thinking you have with these autoregressive models is at least a little bit of an advantage there. Yeah, for now, I don't see a really good reason to bet on a different technology. That could, of course, change, but for now, that's my take.
If I did some, here we have.
After 2 or 3 years, we couldn't live without Claude, Gemini, ChatGPT. Now, I'm worried about the malicious usage. For example, STT TTS model easily copy the voice, so it could be used in voice phishing, such as. So we needed to have some countermeasures or some preparation about that. How about your opinion?
I think when I use like an image model, there is a watermark from that show from the AI, and then I think I'd like to ask my professors, and then when I have a baby in my house, and then there is a lot of a book. The book when I click one book, when I click the book, there is a sound about dog. I also have a dog. When I when my puppy listen the real dog sound, he can like growling, and then he bark. But he listen the sound from the book, he just don't don't give any like a reaction. So I think there is some point that we can develop, and then we can distinguish these two voices. So could you?
Yeah, I think you're mentioning kind of watermarking techniques, right? So people really study about these fields where they intentionally put really small watermark on the outputs, and where human being cannot distinguish two different voices or faces generated by models, but somehow some detector model knows about the watermark that is hidden under the model outputs and figure out. So, but I truly agree with this is kind of half solution, because we do not have such detector on our phone. But I think if it goes serious and serious again, then somehow I think governments or some other regulatory will provide a solution to avoid this. But this is something we should study, I think, in the future.
Maybe I'll just add, I think that this is like a for now kind of a problem. It's a transient problem, maybe, in the sense that the technology has arrived very quickly and we haven't been able to kind of react properly to it. I think there are technological solutions and social solutions out there. Keep in mind that we've only had photography for a couple hundred years. We had ways of verifying things before then. Maybe they weren't perfect, but I don't fundamentally think that this breaks society. I just think we need the tools, and they have to come. And we're living in this period of time where we have these kinds of generative methods out there, but not necessarily the tools to build back the verification. But ultimately, I'm pretty optimistic that we'll solve that.
I'd like to add some interesting episode I experienced. It was like 2022 winter. Only after 1 or 2 weeks after the ChatGPT comes out, I had a talk to judges, 대법원 판사님들, 고등법원 뭐 판사님들 대상으로 세미나 했는데, I had a seminar to judges in Korean court. Only after 1 or 2 weeks after ChatGPT, the first question after my seminar, the judges, like 60s or 70s of their age, the first question is, how can we detect this evidence is generative or not? So it's on 3, 4 years ago. So judges already think about this issue very seriously right after ChatGPT comes out. So I don't know this current status, but people are already think about it and maybe find a way, as process says.
Right, I think we have time for one last question. Any?
Thank you. My question is for Anthropic. My research is on ethics of AI, and I am very curious about to know how you work with the ethical governance that I know that you work with sociologists and philosophers, and I was wondering who should decide of this ethical principle when your models are deployed globally, and how do you balance Western ethical values with those of other cultures? Do you have a specific ethical principles for that?
Yeah, frankly, during our like a we have like the principle for the UN, this kind of things. So we try to like have a like general policy and rules that the model have to follow, and then there are a lot of like discussions, and there are a lot of like our own rule the model have to follow, and then for this question is really hard to answer clearly. So yeah, I think I can give you something more information after this session about that. Yeah.
Actually, we had another audience want to give questions. So.
First of all, thank you for your presentation. For me, most struggling part of the AI research is the high-performance tuning things. It has evidence because the research shows what's the better parameters. But in my perspective, harness engineering is worse because it doesn't have any evidence. It is kind of empirical things to prove what's the better. And as I know, the cloud is not so adaptable for other harnesses except for cloud code. So the thing I wonder is, do you guys think the harness engineering remains as a part of empirical part of do you think it can be developed? It can be developed to like some theoretical part, like deep double descent was a kind of empirical things, those, but it is now kind of proven by theoretically. So I wonder what's your opinion about it?
Just a quick answer that definitely cloud code is the best thing to use the cloud model, but we also provide like a public repo to use harness with just API, other API. So in my case, I guide them. If you want to use your own model or other model, just reference our harness repository and then try to have a try to test and then check the result, and then you can change the prompt or harness and then things, because it's a public repo. So please try to the repo and then with your model and then check it. So we don't want you to use only cloud code. We also want to you can make something very fancy thing. So yeah, that's our yeah.
And at the really early stage of the frontier AI model comes out and harness engineering emerges, many AI researchers also think that, oh, it isn't scientific research. It's just the engineering part, because we just rewrite the prompt or redesign the framework. But more and more researchers tend to move forward to the such part of the engineering for better deployment of the AI and improving the quality and accuracy. So I hope there will be a more systematic evaluation framework and improvement framework for more scientific research. Yes, so this area needs attention.
Can you give an example of a kind of a theoretical question that you could ask about a harness? There was that. I think that was the kind of the question of like to what extent can we apply theory to these harnesses?
Nothing comes to my mind at this stage.
Me neither, but yeah.
Okay, great. So I think we should end here. Thanks for sharing all the insightful thoughts, and thanks for participating in this discussion. And let's end with a big rounds of applause.
Okay, good afternoon, everyone. The track sessions under the theme of the physical AI and embodied intelligence is about to begin right now. So please make your way inside the room and have your seat, please. Okay. And also, before we start, I would like to announce that you would be appreciated if you could turn off your mobile phone or in silent mode for the remaining event. Thank you. Okay, so it's time. So let me start beginning our session. So yeah, good afternoon. My name is Hyunjung Shim. Okay, I'm from the Kim Jae-chul Graduate School of AI at KAIST. So today I'm going to moderating the sessions. And it's my pleasure to serve as a chair of this track D. And as I just mentioned you, the title of today's session is Physical AI and Embodied Intelligence. So today we are pleased to welcome leading researchers and industry experts who will share their latest research and insights into physical AI and embodied intelligence, exploring how AI sees in 3D things on the device and also acts in the real world. Okay, I hope today's session will provide you the valuable insights and provide some meaningful discussions. And please also be noted that the session will be live streamed on the official YouTube channels of the Global AI Frontier Symposium 2026. Okay, and then now I'm very much proud to announce our first speaker. Okay, please join me in welcoming Professor Minsu at POSTECH, who will deliver a presentation titled Toward Open Vocabulary Grounding and Grasping for Embodied AI. Please give him a warm round of applause.
Yeah, I'm grateful for the kind introduction. So before getting started, so I'd like to say two things first. First one is this is actually my original title, but due to the lack of time, I decided to focus on the first topic. So now this is my title. So, and the second thing is, I'm a computer vision researcher, better than robotics researchers, who is focusing on this active perception and robot vision. So yeah, don't be disappointed that I'm not showing you very fancy robot demonstration and experimentation. Yeah. Okay, today I will present my recent work on this topic, open vocab, 3D grounding and grasping. Yeah, I mean, this talk will include two of my recent papers. First one is Affogato, which will be presented in upcoming ECCB. The second paper is this Affostruction, which has been already presented in this year CBPR. Yeah, then let's get started. So, as all you may know, so one of the hottest keyword in AI would be arguably this embodied AI or physical AI. So meaning that the AI system interacting with the real world environment. Yeah, this has been dreamed of for a long time. And this image is from an old movie by Centennial Man, where the robot is serving people in the dining table, as you can see. Yet to do this job, so the essential ability is to understand the arbitrary object in the scene based on some arbitrary natural language instructions. So that's the topic I will talk about today. So to explain my motivation, so there has been a huge surge of end-to-end visual language action models that leverage larger scale foundation visual language model, large language model, or video generative models. Using them as a sort of high-level planner. So, so this is actually showing very brief history of recent development of robot learning. So starting from this task-specific reinforcement learning or imitation learning, so it has been evolved into this language conditioned policy. By scaling them, so we call this foundational vision language action models like RT1 or RT2, this robot transformer. And then in recent years, so many big tech companies has been investing in a lot of money into making this vision language action models at scale. So now you see, those models like Groot and Gemini robotics. This actually basically bypasses traditional modular stacks, allowing the brain to understand the sort of instruction like picking up, and involve very specific visual recognition and mechanical control in one step. So then, how is the state of the art? So do they generalize well to unseen tasks in unseen environment? Actually not, as you can see from these examples. So basically what happens is like the visual language action models works very well on atomic tasks like very short horizon manipulation task, but when we ask them to act on a long horizon task, basically it often fails and still it lags behind just conventional robotics models. So basically when you think about this, the visual language action model performance is degrading a lot. So when we ask them to act on structural or compositional manipulation. So there has been a bunch of benchmarks revealing this limitation of visual language action models. For example, a recent benchmark for compositional generalization capabilities, especially in this long horizon manipulation, demonstrate that the visual language action model's performance degrades as the structural and compositional demands increases. So here, this composition means different combinations of object and environment and atomic actions in testing time, different from what they have seen in training time. So these two plots shows that trend. So briefly speaking, the plot on the left shows the performance of compositional generalization is all poor and does not improve with more data. And the plot on the right reveals that the visual language action models generalize to atomic tasks with more data, but not to compositional and long horizon tasks, even with more data. Then what do we need for better generalization? So I would argue that we need this visually grounded reasoning in 3D. So let's take this example. So when the robot is asked to do this instruction, like open the top open door, it has to do some reasoning, right? The first, it has to find the top open from the scene. And then it has to find its somehow relevant part for opening this action, which is actually the hook. And then finally, it has to pull the hook to open each door. So that's the sequence of actions it has to perform, to do the job. This is actually not a trivial sequence of actions. So, and at each step, as you can see, so the robot needs to be able to visually ground on the corresponding elements in the scene, and it has to be open for real-world environment and object and actions. So now, we can think of the following natural and basic pipeline of the grounded reasoning process. So given the query, in this case, open the open door. So the first we have to do this instance segmentation, this localization of the corresponding object. And then we do this object part segmentation, which is actually affordance grounding. And then we have to perform this grasping and action at the end. Yeah, this is what I call visually grounded reasoning in 3D. So for that, I think we need at least 3 components. The first one is explicit 3D representation for better spatial reasoning. And the second thing is the interpretable grounding from natural language instruction. And the third thing is grounded and embodied reasoning chain for action, proper actions. So those tasks are actually what our group is focusing on these days. And among these tasks, so I'd like to talk about some work on, my recent work on this open vocabulary of affordance grounding that is tackling this middle part of this pipeline. Okay, then let's get into it. Yeah, so let me first explain the task. So this terminology, open vocabulary 3D affordance grounding, is the task of localizing affordance-related reasons from a 3D object given a text query. So for example, given a query like if you want to lift the bag, where is your finger most likely to carry it? And then the model should consistently localize the handle reason across these very different back shapes. So as you can see here, this reddish reasons on the surface are the target output. Yeah, but this is actually, not that this is not actually a segmentation mask, but the heat map output. So reflecting the intrinsic ambiguity of the possible contact reasons in this affordance. So it has a form of probability distribution because you can choose any point of contact. So when you perform the corresponding action. And this term, affordance, comes from, originally comes from the Gibson's ecological psychology. And it was actually the broader concept that refers to the action possibilities an environment offers to an agent. But here, the task is just focusing on the contact estimation for manipulation from a more like object-centric viewpoint. And yeah, this term, open vocabulary, refers to the capacity of processing a natural language query without restriction to a fixed number of classes or template description. So that's what I mean by this open vocabulary. And on the other hand, this is most crucial thing, the 3D grounding refers to the structure of the input and the output. So basically it takes text query, and then, so we'd like to output this corresponding contact reason estimation. Yeah, so that's what I mean by grounding. So actually this task has some challenges. So actually there are many challenges. So among others, there are actually the main 2 challenges. First one is the issue of data scarcity and the issue of partial observation. So let me tackle by one here. So here, the first issue is the problem of data scarcity. Prior work mostly relied on this PartNet-based data sets, such as 3D affordance net and OpenAD and Lasso. But their scale remains very limited. So they cover only 23 object classes and just like around 15 affordance classes and fewer than 1,000 text queries. So this small scale makes truly open vocabulary generalization essentially out of reach. So to tackle this issue, so we proposed to leverage 2D vision language foundation models to generate the data for 3D, to train the 3D models. So meaning that we actually design an automated pipeline for data annotation. So the main motivation is that, as you can expect, so in this data-rich domain, in this image and language, I mean, because 2D image and text language, so we have very good foundation models, right? And why not leveraging them to annotate and generate 3D data? So that's the main motivation behind this. Okay, so then what is the specific idea? So that's quite simple and a bit boring. So given, let's say we are given a 3D data scene like this, reconstructed or captured. But and let's say we want to annotate where the object is. For example, in this case, so we'd like to annotate the location of a pillow in the scene. So can you find it from the scene? Maybe not, because that's quite small. So you will see that. So what we do is as follows. We first render them into multiple views, which is very straightforward and easy. And now, so here, in this case, you have 4 views, different views. But of course, you can get more, as many as views you want. So since we have these 2D images, so you can use your maybe just random favorite 2D foundation model to localize the object by asking them to localize the pillow in those images. So then, yeah, we can make this annotation in the image. Denoted by this red star shapes, on these 2 images. And then, we lift these annotation masks in 2D images up to 3D by back projection to 3D space of the scene. So that's what I'm doing. And in aggregating them, so we can consider the mask consistency because we have this 3D space, right? So by back projecting those annotation into 3D, so we can leverage somehow this 3D space consistency to prune somehow noisy annotations. Yeah, that's the basic idea. So likewise, we made this larger scale data set generation pipeline. So specifically, this is actually what we propose, called Affogato engine, an automatic labeling pipeline built on foundation models. So we take an instance from open sourced 3D asset. In this case, we use this Observers dataset. And first render the 3D meshes into multiple views, 2D images. So from these images, so we use foundation vision language models, like in this case, Gemma 3, to generate affordance text queries suitable for the object. And then now we have images and corresponding queries. So for each view, we use another foundation model. In this case, we use Mormo. Sorry. A strong pointing model to predict a point corresponding to the query. And that point is fed as a prompt to mobile SAM, which produces 2D mask. And finally, we all lift them up to 3D and vote the mask across views to obtain more like a consistent and reliable 3D affordance heat map. So the entire process runs without any human annotation. So for the detail, please take a look at our paper. So using this engine, so we built large-scale affordance grounding 3D dataset called Affogato 150K. So the largest dataset for open vocab 3D affordance grounding to date. It covers more than 450 object classes, more than 350 affordance classes, and 750,000 text queries. So this is well over an order of magnitude more diverse than the prior data set. Yeah, so as you can see, it looks quite good in terms of this annotation quality and diversity. Yeah, this is some statistics compared to the prior data sets, but we just, skip that. So actually, this is basis for training open vocabulary affordance grounding models. So actually, in this paper, when you take a look at it, we also proposed some baseline models and achieved state-of-the-art affordance grounding performance at the time with very simple baseline models, showing that the scale of our data set and the quality and diversity of our data set benefit affordance grounding. Okay, now let me turn to the second issue. So the actually main topic today. The question here is like, okay, 3D output is great, but is it reasonable to assume a complete 3D shape as an input in practical situation? Maybe not, right? Because even if the robot has sensors like 3D sensors, for example, LiDAR or like LGBT cameras, it's just a partial, right? It's never complete. And even in previous work, actually, the existing affordance grounding methods assume this kind of a fully reconstructed 3D shape. But in real robot manipulation, so we usually have this partial observation from the position of the agent of a robot. So in this setting, the prior methods can only make a prediction on the visible reasons, and the output itself could be heavily degraded by occlusions or serious partial observation. So as you can see in this example, so when the critical reasons remain occluded or invisible, so it severely limits downstream manipulation and affordance grounding. So we propose this abstraction, active affordance grounding with generative reconstruction. So abstraction, this method addresses this issue with generative reconstruction. So the idea is very simple. So the first, we use a generative model to reconstruct the unobserved or invisible reasons, which is like hallucinating this invisible part, and then ground the affordance on the completed shape from this generation. This gives us a very clear advantage if the generative reconstruction works well, right? So we actually designed this RGBD to 3D generation model for this purpose, because in all the previous methods for RGBD reconstruction method have their own limitation. Yeah, so, but as you can expect, so the output reconstruction still remains largely inaccurate because we only have the partial observation in the first place. So, as you can see in this example, even if this partial observation leads to somehow reasonable reconstruction in a generative way, so as you can see, the shape of this this is not that kind of accurate. So to tackle this issue, so we take the active perception perspective and bring it to the affordance grounding. So what do I mean by active perception? So active perception refers to a paradigm in which a perceptual system does not passively receive visual input, but instead actively controls each sensors, for example, cameras or eye, and positions and orientations and all the other parameters in order to purposefully gather information from the environment. So in this perspective, we perform an active cycle of reconstruction and grounding. So what we do is as follows. So after initial prediction of affordance grounding, so we can simulate an action that takes another observation, a new RGBD frame, to better ground the affordance based on current estimation. You see? So in this case, the purpose for action is, of course, better grounding. In that sense, we can call this as active perception. So this can be simply done by searching for the camera position where we get the maximum visibility of the estimated heat map, right? Of course, there might be some other methods for selection, but this is what we have used in this work. Then, okay, we navigate to that position to take another view. So here in this example, the actionable part can be best viewed from the top. So we navigate to that position to take the second RGBD frame. So that's what happens here. So this gives us better reconstruction of the actionable part so that we can get better grounding as well. So as you can see from this example now, this sort of light stand has better reconstruction, which makes, in turn, better grounding. So this chain can be iterated, of course, until we get a sufficient coverage of surfaces or grounding certainty. So, you can design this scheme in a way. So in this way, we actively and progressively improve both grounding and reconstruction at the same time. This is actually the overall framework we propose called abstraction, a blend of affordance and reconstruction, as you can have guessed. So, this is actually some more detail about the pipeline. This abstraction pipeline has actually 3 steps. I will just fast forward. The first, the generative multi-view reconstruction. So from RGBD observations, we generate the complete sparse structure of the object. The second, flow-based affordance grounding. We take the sparse structure and then a text query, which is actually instruction, and then predict a 3D affordance heat map. And third, the affordance-driven active view selection, which I explained earlier. You see, based on this current heat map, we select the most informative next view and obtain new observation, and then repeat. So let me walk through each module just briefly. So for generative reconstruction, we first extract 2D feature map using, in this case, Dino version 2 from each RGBD view and fuse them into 3D space as a sparse voxel using this depth information from RGBD. The main design principle here is to create an explicit 3D space to effectively aggregate these multi-view features into a space regardless of numbers of the views. So this multi-view processing capacity turns out to be very crucial for active perception and sort of incremental inference. So the more views we observe and the better grounding we obtain in this scheme. So these voxel features serve as a conditioning for the flow-based transformer trained with conditional flow matching. So on the right, so you can see the architecture. So this sparse VAE encoder and the decoder are built on this 3D shifted window attention. I will skip the detail. The second stage takes the sparse structure and the text query and predict the affordance heat map, as I mentioned earlier. The key idea here is to formulate grounding as flow matching rather than just deterministic regression. So the reason is that the affordance is inherently ambiguous in many cases. For example, where you would see it can plausibly distribute over many parts of the chair, the bag, and armrest, the others. So the flow matching methods naturally capture this kind of multimodal distribution and a sort of stochastic nature of grounding. And so at the bottom of the slide, you see this loss we used for training that combines, binary crossover entropy term and this dice term. Yeah, skip the tail. And then the final third stage is active view selection. Given the current 3D heat map, so we render it from each candidate camera pose and define this visibility score as some of rendered this affordance probability over pixels. So we then select the view that maximizes this score and navigate to it and capture a new RGBD frame and run reconstruction and grounding again, iterate. So by actively navigate to this position where the affordance is most visible, so we can achieve robust reconstruction and grounding with only a few views. So that's what happens here. So this is actually experimental result. So we evaluate our method on affogato benchmark. I explained earlier in the first part of my talk. This is just for partial observation setting. So the metrics we used here are this average IOU, average chamfer distance, computed between this predicted reason and ground truth point clouds across this heat map threshold. Actually, there are some baselines that apply affordance grounding directly to the partial point cloud. And they, as you can see in this table, perform very poorly. Combining them with reconstruction models like Trellis and MCC, a little bit help, but only marginally. In contrast, this upper structure reaches amazing performance. And that's roughly like twice of the longest baseline performance. And it achieves the best chamfer distance metric overall. And these are some example output for partial input, such as the stool, and And you also see this diverse queries like a sit on and support your feet and handle to carry and sign indicating hazard. So every one of them you can see that the construction reconstruct crowded geometry pretty much well, while localizing the semantically correct affordance reasons. So that you see here. And these results show that we can get better grounding along multiple rounds of active perception I explained indeed. So this example is the problem where given a side view of the fireplace, we are actually asked to point to the part we would place logs in. This is challenging because only a small part of the fireplace is visible from the current position, right? But our framework allows us to hallucinate, in a good sense, sure, the invisible part, which is, not so bad, and takes a better view to predict the better grounding in the next step. So on the right, so we quantified this effect on the whole data set, comparing this average IOU against the number of the views. So as baseline, we used just sequential and random sampling. So our active perception strategy, the red line shown here, converges to almost nearly peak performance with just 2 or 3 iterations, as you can see. So it shows that our active perception of construction, significantly improves the performance in this practical setting. So we think our framework can be directly applicable to embodied AI problems in many cases. So after doing this affordance grounding, what comes next? Of course, yeah, we should leverage this result for next step, which is open vocabulary grasping and actions generation. But yeah, for the lack of time, I won't go into the detail, just a small teaser here. So what we have shown in our CBPR, listen, our CBPR paper this year is that this visually grounded and embodied reasoning step by step is indeed more effective than directly generating grasping and action. And furthermore, there are some other advantages as well, like better interpretability and better controllability. Yeah, if you are interested in the detail, so please take a look at our paper, Dexter. Yeah, and this is my final slide summary. I argue that visually grounded reasoning in 3D is crucial for embodied AI. And we introduced some basis for that. This open vocabulary 3D affordance grounding, which is avocado. And we also propose this active perception strategy that integrate this affordance grounding and reconstruction, which may be a very practical approach in real-world embodied AI. Yeah, that's it. And thank you for your attention. And I will be happy to have questions if you have enough time or if you have any question. Thank you.
Thank you for your excellent presentation. It was really wonderful work, right? Now we are going to have a few questions from the audience. If you have any question, please raise your hands. Then our staff member will approach you with the microphone. In the meantime, I kind of have a question to you, Professor Joe. So it seems like you give us this very nice affordance annotated 3D data sets, right? And then after that, you told us that how we utilize that, right? To actually affordance data set. And I mean, the affordance itself can be a very great clue to, I would say, ground this partially observed data. I think that's main flow of your. Yep. So yeah, I kind of agree. And in other words, I also thought about this way. Well, developing such a 3D assets with the affordance annotation, I think the most straightforward way is just bringing so many 3D assets based on its class label. We can actually guess what kind of affordance we can assign to it. If we do such a naive assignment on affordance concepts to the object, will that work or will that simply fail? What's your opinion?
Yeah. Thank you for the good question. So, it depends on what are that naive methods is. I mean, so basically, so when you take a look at our pipeline, so we carefully designed this pipeline that can effectively generate this annotation from just a 3D asset without any annotations. Yeah, actually, in doing so, actually, we have tested many naive approaches to generate those annotations. So, of course, you know, almost all of them were quite bad. So, in that sense, I think our method would be maybe one good strategy to get, you know, good quality of annotations. But of course, this is not the best one. So you can, you know, develop better ones.
I see.
I hope.
No, I'm not. Yeah, that's actually a very good idea. So, and another question was actually at the beginning of your talk, you talk about this difficulty of long horizon task, right? So how does that can be possibly, you know, resolved by this affordance concepts?
Oh, yes. So basically, regarding that question, so basically my, I mean, the solution is not enough, of course, but so as I have shown in the middle of the early part of my presentation. So at least we have to have some kind of some explicit pipeline that simulate our cognitive process. For example, when we are asked to find and do something, so basically we first localize the corresponding object and corresponding reason, and we perform an action on that, right? So I mean, most of the vision language action models just perform all of them together in a very big black box pipeline, just single end to end. I think it has some merit, but it could not be well generalizable to sort of more complex tasks with more complex compositions. So that's what I meant. Of course, this is just a starting point, I think. So to better perform, so maybe we have to make somehow more complicated and reasonable, proper reasoning process as to simulate maybe our cognitive process in performing some actions. I mean, that's actually open problem, sure.
I see. Thank you. Any questions from the ground? Okay, to hear we have a question, please send him a microphone.
Thank you for the great talk. And the DexDR seems really great application of those affordance-related works like Affogato and Obstruction. Well, it was talked very little. And my question is that, is there any real-world robotic hand result of DexDR, or do you have any plan to apply it? And I'm also wondering that, do you think that DexDR can generalize to any object or like robotic hand embodiments?
Yeah, thank you for the question. We are working on it, as I briefly mentioned earlier. So I'm not a real robotics guy, so I'm just trying to expand my research topics to robotic vision. And so we are actually preparing to transfer this method to real robot environment. So we are building a real robot in our lab, and we are trying to, apply our method in this real situation. But we didn't get that yet. So next time, so when I do another presentation, I will bring them together. Not to disappoint you. Sorry for that.
Thank you.
Yeah.
Thank you. Any questions? Yes.
Thank you for your great talk. It was very inspiring. And I have a question about the long horizon manipulation and tasks. Of course, affordances and some kind of skill kind of labeling is also important, but also I think the context length is very important. So thinking about the Claude, it has to compact its conversation during the chat so it can have enough space. So do you think if the same thing could happen during the manipulation of the robot? And if that's the case, do you think is there any solution for that?
Thank you for the good and very difficult question. So I have to say that actually our system, when it comes to this efficiency and latency, it's not performing very fast. So we're actually relying on this sort of, oh, okay, I didn't explain the detail of this Dexter and this grasping models, but actually it is using actually sort of large language models and this autoregressive generation. So because of that, it has a problem of efficiency. So if you want to enlarge and if you want to expand this reasoning chain in a more detailed and more like a proper way, of course, we have to boost this speed to perform in the right time, because when you're performing actions, basically this timing is very crucial in many cases. So, but I'm not a real robotics guy, so yeah, I'm working on that, and maybe next time, maybe I could bring a proper answer to that question. Yeah.
Thank you. Actually, after this, during the panel discussion, we were gonna talk about how we make things. I mean, thinking fast on device. I think at that time we can kind of share some great insights regarding that too. Okay. Any other questions so far regarding his talk? Yeah, the one last chance. Okay. Actually, yeah, by the way, we are kind of reaching up the time. So thank you very much, Professor Joe. And yeah, we should give him another round of warm the applause, please. Yeah.
Thank you.
Thank you very much. Okay. Yeah. And now let us begin this panel discussion. We have to rearrange these chairs, so give us a few minutes, okay? So yeah, during this a few minutes, you can go to the restroom and stay up. Yeah. And we are gonna start in a minute. Okay. Yeah, we will start at 45. So yeah, please give us a few minutes. Okay, good afternoon, everyone. So now we are about to start this panel discussion session. Yeah, so before beginning today's panel session, I would like to introduce our panel. So from left to the right, yeah, I'm going to introduce, but then if not enough, I will give you the mic and then introduce yourself if it's not enough, okay? So the first panel here is Erin Jungmin Lee, the AI Strategy Team Lead at the HD Hyundai. Okay, yeah. So here she is. And then next panel, Ming-Sheng Yang, professors at University of California, Merced, and he's also affiliated with the Google DeepMind. And then this third panel, the Youngjun Kim, the Senior Vice President, Head of AI Lab at LG Electronics. And finally, we have Il-Young Yoon, Senior Vice President, Head of AI and Robotics Convergence R&D Lab at POSTECH Holdings. Yeah, so these are the experts from both academia and the industry. So I'm very excited that we are going to have a meaningful discussions both in academia and an industry perspective. So yeah, so I would like to actually toast today's topics. Actually, we will be given this session with the big title, Singing in 3D, Thinking on Device and Acting in the Real World. So basically, we will start with this singing in 3D first. This topic will be mainly about how we obtain the data from, so training data, where that data should come from. And besides, we will also talk about how we learn the physics, okay, physical law and intuitions. Is it should come from this built in by hand, or we just learn it from the scale? Those are the things we were going to discuss. And that's for the singing in 3D. And then we were going to move on to this, the thinking on device. So one other, actually, the question was about this inference speed and how make it efficient, right? So here we're also going to talk about, especially in robotics applications, sometimes this inference time is not just for user satisfaction, like a AI chatbot. It's more like hard limit. So if we don't make it in time, hard time, then this process completely fail. For example, we have to catch the falling pen, we have to make in time, otherwise it fails, right? So here, that's why we need to think about how can we make sure that our AI robot actually think fast enough, even on the device. Okay, so that will be discussed. And then third, this is going to be a real, acting in the real world. So here, I will more like talk about, well, we mostly focus on the visual data when we analyze the scene and understand the scene. Well, that will gonna tell us how it looks like, what that means. But it doesn't tell us like how we can grab the things and using the right amount of force to grab the thing or stop the thing. So toward that direction, what other sensory data we need? That is going to be discussed for the final. And then after that, we are going to talk about what are the main, actually one thing that can change this physical AI moving forward. So those are the main topics that are going to be discussed in the sessions. Okay, so after that, we are going to start with the very first questions. Okay, so my first question is the training data. Okay, how we train the models with what kind of data. Okay, so I think nowadays people mostly talk about the three sources of data. One, simulation data. Basically, Cosmos actually utilize that. A second types of data would be the internet scale video, where this VJPEG-2 actually approaches to. And third is more like a robot itself collecting its own data. Okay. And by the way, other than having three different types, more recently, this GROOTN1 like models utilize all different kind of data, sticking them together and then developing the mixture training strategies. So here is my question to the panel. Will such a mixture training would be a right approach? Or as we have learned from this LLM era, just sheer amount of data, but this high quality collection, for example, robot collecting data. So if we have so many, will that be sufficient? Okay, so I will start from the left to the right. So please, Jungmin, do you have any idea to this question?
From the perspective of heavy industries, physical AI cannot converge on a single recipe, I think. So hierarchical mixing principle is the only resilient path for the harsh environment, I guess. So internet video, as you mentioned, can provide AI with a visual common sense, I guess. However, no matter how many millions of hours of YouTube you watch, you will never find the high fidelity kinetic feedback that needed to mate massive hull blocks or hydraulic forces, for example, for inside of the 30-ton excavators. So the internet simply doesn't have a kinetic data of heavy machinery. So on the other hand, relying 100% on the world data collection itself from a heavy assets, it's economically and operationally, I guess, impossible. So in our specific domain, a single data failure can lead to a multi-dollar damage or even fatal casualties. So raw real-world data collection is just too high risk for us. So I think many manufacturers, including myself or my company, will deploy the hybrid pyramid strategy. So we leverage the internet videos to actually see the basic physical common sense. Then we use physics-based simulations to safely scale millions of dangerous scenarios. And then we top the pyramid with a real-world kinetic data from the actual machinery to actually bridge the sim to real gap. So I guess in conclusion, while the data volume is still the king, we'll build the skeleton with the internet data and also then expanding scale through simulations and then locking in precision with exclusive field data from our shipyards and industrial sites. I think this hierarchical mixture is the most proven path to scaling physical AI in heavy industry.
Oh, thank you. Thank you for the very much insightful discussions. And yeah, so that's from this industrial perspective. Now, Ming-Sheng, so do you have any kind of more recent research perspective to this directions? Oh, I think you can just talk. Yeah. Try to talk. Yeah. That way.
Oh, okay. Sorry.
Yes.
Yeah. See. Okay. Well, I think enough being said. I mean, I think yeah, it's true that we need to use some simulated data just for the sheer amount of that, and then yeah, you won't be able to cover everything in real world. So yeah, a good mix of that would be good. I don't know the good recipe of that, but certainly nowadays it's easier to generate data from all kind of model, right? So then that should give you a good sense of what's going on and how you want to train the model. And then, if that's not enough and if it doesn't work well, then you certainly would add in some real world data to do that. I mean, in a way, it's like in the old days for the debate on label data, unlabeled data, and weekly label data. I think we can draw some analogy from that.
I see. So, by the way, so I think you made a good point. Like, even though we think this LLM or our vision foundation model is kind of developed it and then improved with this large scale of data. In fact, if you look at closely, their training recipe is not just high quality annotated data. Actually, they are mixing up with this weekly label data and all together. So Ming-Sheng might talk about that, right? So we are anyway going to use whatever data types available to us to train the model. Yeah, that's a good point. So then next, please, yeah, the go with this first question. Youngjun Kim from this LG Electronics. Yeah.
Yes,
Please
I
share
think the answer has been changed quite a bit over the past year, and until recently, many of the community focused on collecting the data, collecting behavior cloning data, and which it can turn the vision data to action, and but through the teleoperation. But that we have driven a lot of progress about that, but it has a certain limitation for that. We have now seen the big scale data like ego scale. The NVIDIA has mentioned about it, and we in that data we collect data from using the VR gadget and the handcrafted globe, and which can make us to collect data much naturally. Yeah, so it's very efficient to gather and close the gap between the simulation and the real world data. And that's the one approach we can try to. And I believe the scaling law will continue to improve robotics general manipulation capability. However, the vision and the motion alone are not sufficient. Human relies heavily on their touch and physical information. We as a human knows when an object is sleeping and how much force to apply, and whether something is soft or rigid. Not only because we can see it, but because we can feel it. That's why we believe the next frontier is the sensory intelligence. We need to incorporate the modalities such as tactile sensing and the pulse feedback into our learning systems. We see those low-level latent sensory capability as a separate layer of intelligence. They should operate almost like reflexes, handling faster physical interactions locally, while higher level foundation model focused on reasoning and planning and more long horizon decision making. In other words, the future is not simply about collecting more data, and it is about collecting richer data across multiple levels of intelligence and building architecture that allows those levels to work together seamlessly. I believe that.
Thank you. Thank you for the talk. And then could you go with this
Yes.
question?
In conclusion, I think we need as many modalities as possible. But I would add one thing. One key difference between RFM and LLM I see is that the current robot foundation model are trained as a collection of specialized modules. Different modalities are typically learned separately before being integrated into a final policy. On the other hand, LLMs are trained or built mainly around a single self-supervised objective. As you know, next token prediction. So I think robotics will eventually move in a similar direction where different modalities are jointly learned under a unified objective and a unified representation. I think there are two major challenges though. The first is data. As we all know, robotics doesn't have enough real world data to support LLM scale self-supervised learning. The second challenge is architecture. People working in the industry like me tend to prefer modular and explainable systems even if they are somewhat less efficient. In safety critical applications, fully end-to-end system will probably take much longer to gain trust. So, but that said, if we really want a truly general purpose robot foundation models, they can perform almost any task. I think an end-to-end approach will become much more important direction. My guess is that this will become possible only as simulation continues to improve and only as large-scale robot experience data from many specialized tasks is collected into a unified data set, I think.
I see. Okay. Thank you for your ideas and discussions. And by the way, I realized that each one of you might have different robot application in mind, perhaps. So let us first. So what applications do you have in mind in your industry side? Can you share with that? Yeah. So starting from the Young, yes.
First,
Oh, yeah, okay.
we have planned to send our robot to the factory to help people to operate and build some kind of product, and we collect a lot of failure data and the recovery data from those real factory, and then we upgrade the model and validate the safety, and finally we want to send our robot to the real home data, because as you know, LG is very good at selling the home appliances, and we hope that the robot and the home appliances can work together to help people with no zero labor home. Yeah, that's our vision.
Regarding that two different application scenarios, I think the required training data and is quite different, isn't it?
Yeah, quite different.
Yeah.
But the essential data is, I believe, the same, because we need the very sensitive tactile sensing data and the vision data, and how can we recover from the failure, and that kind of data is very common, even in the factory and the homes environment.
I see. Okay. So what about you, Ilya?
Yes, I work in the process industry. So we are figuring out the applications to operate the industrial equipment, but it's a little bit hard because the current humanoid hardware has limited capabilities. So we are looking forward to finding the right applications.
I see. I see. Okay, so humanoid versus more like industrial robots. Can I say that? Okay, and then
Yeah. We are using many industrial robots
Yes.
in the factory floor, but there are many applications that needs humanoid or mobile manipulators. So we are looking forward to finding it.
Okay. So what about Jungmin? So the heavy industry.
So I work for the HD Hyundai, and HD Hyundai is as you know, global leader in the shipbuilding and construction equipment, and also the oil refinery. So I guess our mission is to actually turn a promise of physical AI into a reliable commercial reality, because specifically engineered to operate safely in a harshest environment, which includes our shipyards and industrial sites. So that's our focus.
I see. So try to help your workers. That's mainly the focus. Okay, so now we kind of figure out the robot application for the industry side. Good. Okay, knowing that, okay, so thanks for sharing your idea about the training data. And mostly, I think many of you kind of agree that mixture training strategies is now the feasible solutions. And then let me move on to the second questions. This is regarding how we build this physics into the model. So my initial question was, do we really fit that physical law inside the model, whatever hard coded, or try to enforce it? Or just learn it from the scaling, meaning the large amount of data can naturally lead us to learn about it. So which one you think more feasible way? And if there is any, effort in your side, either industry or research side, you guys can share your idea. So can we start from, Jungmin, yes,
Oh,
please.
okay. So I think it really comes down to the domain. So because the level of the physical precision required varies significantly. So in heavy industry like the HD Hyundai, such as our industrial sites or shipyards of HD Hyundai, the requirements are completely different. So let's say we're bending massive steel plates for the shipbuilding, then we just cannot rely on the plausible movement, right? So we need precise engineering figures, and we need to know exactly how many millimeters a material will deform under a specific load. So in addition, acquiring such an industrial site data on a large scale is practically impossible. So at the same time, visual data cannot capture the internal states of the variables like plasticity and locked-in stress. So maybe like two still massive plates look identical to a camera, but still their actual physical state are completely different, maybe completely different based on their deformation history. So you cannot simply see the internal stress or temperature history through the lens of the camera. So relying solely on the explicit physics is not perfect either, as you know, because the pure simulators rely heavily on simplified assumption due to the computational limitations. So from an industrial standpoint, for my perspective, the most practical path is to hybrid approach. So we use physical laws to actually define the hard boundaries and ensuring the model stays within the realistic limits. And then we leverage the data-driven learning to compensate for the real-world friction deviation or model form errors. So I guess the integrating data with physical principle is how we truly close the gap.
Yeah, good point. Thank you. So Ming-Shin.
I think they can answer better than me because.
That's right. So
I can add something later.
Right. So
Please.
please, Hyunjung, please.
I don't think this is a choice between explicit physics and large scale learning. I believe we need both, but for a little bit different purposes. Large scale data is excellent at capturing statistical regularities and learning general physical intuition. But it allows our models to acquire broader knowledge about how objects move and interact. However, I believe the explicit physics remains essential in at least two important situations. First is after the deployment. When a robot is rolled out into a real world, failure cases often arises from subtle physical mismatches, contact dynamics and friction, or material properties. Those are difficult to learn perfectly from the data alone. In many of these cases, introducing more accurate physical models or constraints helps us diagnose and reveal failure cases much more efficiently. The second case, during the data generation, as synthetic data becomes increasingly important nowadays, we also need reliable ways to evaluate whether simulated behaviors are physically plausible. Physics-based simulation provide a mechanism to validate and improve synthetic trajectories before they are used for training. So in my view, physics is not replacing data-driven learning. It acts as both a debugging tool after deployment and a quality assurance tool for synthetic data generation. I believe that.
Yeah, thank you. Actually, my question was a bit stupid, right? Choosing one of these two doesn't sound good, right? Yeah, Hyunjung, please.
Yes, I agree with the
yeah.
other panelists. I would add something. My team also developed the physics-informed neural network for process control. So this is a topic I'm personally interested in. At least with today's technology, as others mentioned, I don't think video alone is enough to learn accurate physical knowledge. It may produce results that look plausible, but the producing physically reliable behavior is a different challenge, especially for robot control. Of course, simulation can be alternative, but simulation isn't perfect either, I think. Contact, friction, and data property, material properties are often to model, often difficult to model. My view is that physics-informed methods provide a strong inductive bias for extrapolation beyond the training distribution, but data-driven methods are generally stronger within the distribution that they've already seen. So I don't see two approaches as competing with each other. Instead, I think combining explicit physical knowledge with data-driven learning is the most promising direction.
Okay, thank you. So all our panelists can suggest us to use the strong physical simulation data in addition to this, actually the scaling, the whatever the real data available. So combining together, I think all of them agree to choose. Okay, by the way, before I move on to the next question, if you have a question regarding first and second, well, I can kind of take your own questions or your idea, your opinions if you have from the audience. Yeah. Oh, right. Yeah. Please. Do you have any microphones from the staff? Staff, do you have a microphone? If not, I can give you mine.
Before moving to next section, I would like to ask about the regarding data set. Professor Sim already mentioned about simulated data set. Recently, in case of a hospital and some data is hard to gather in real world. So based on digital twin and the synthetic data set is booming up. So how about the kind of gathering data set is valid or invalid? I would like to hear the opinion about that.
So the question was about like using synthetic data. It seems kind of the popular nowadays, right? So any particular methods they are using to simulate the data? Is that your questions? So I think each domain has a different simulation scheme set, right? So do you guys have enough simulator, or is simulating data itself is difficult and research problem? Yeah.
I think it depends on the type of sensors. In my experience, the only sensor that I have confidence almost 100% is LiDAR. LiDARs in simulation, especially Isaac Sim. We have used the DSS in Isaac Sim a lot. So the LiDAR measures the depth. So the depth data is reliable in my experience.
I think the answers to your question is depending on data, but some simulation data is very good, then they will take it. I think that's the questions. And any other questions from floor? Yeah, if not, then I will move on to this third questions. So third question, which is interesting question, is about this inference speed for real-time actions. So yeah, as I earlier mentioned, some application is really critical regarding this inference time. For example, I can give you this falling pen, catching falling pen as an example. If we don't make it in time, then, pen falling and, the task is incomplete. I think a similar situation can be like a human and robot interaction. If it doesn't meet this hard time limits, then we cannot complete the task. So to this direction, I think this inference time is very much critical. So here, especially, we should make sure it works fast enough, think fast enough on the chip, okay, on the device. So toward that directions, any effort or idea regarding how we make the robot think fast enough on the device? Can we start with this, Jungmin? Right.
Okay, so I think I believe the architectural approach must differ based on whether we're building a general purpose humanoids or deploying robots in a very specific industrial settings. In heavy industry, while perception is highly complex, but the required actions are often highly structured. So I guess, for example, like crane hoisting or welding automation, the visual perception difficulty is immense. I mean, the model must recognize people in large structures and also the load weight in real time. But final control actions can be represented in relatively low dimensions with just a few degrees of freedom. So I guess in this case, directly applying the high dimensional raw action generation is highly inefficient. So I guess the most realistic approach is to adopt a hierarchical architecture that utilize traditional controllers as a prior. So instead of generating action from the scratch, maybe like using the AI foundation model should only perform the residual corrections and parameter adaptations layered on the top of the nominal trajectories that existing physics-based controllers have already verified. So this principle also applies when humanoids enter manufacturing, I guess. So we should let field-proven systems like NPC or whole-body controllers handle tasks like posture stabilization or collision avoidance, while VLA should focus only on the high-level decisions. So successful real-time control is not just about like model lightweighting. I guess true solution lies in the hierarchical structure that uses domain knowledge to actually optimize the action space. So in actual work environments, I think the stable control structures with strictly bounded latency is always the top priority.
Thank you. And I think this kind of answers can be only obtained from the industry, I think. So it's very valid and valuable.
Yeah,
So
I was going to say that. Yeah, that's a luxury of being in academia. All you need to do is to write a paper based on, you come up with some method. As long as you have enough GPU and you can train it, you can run it, that would be fine. But I also work at Google, so I also understand that, in some application, you do need to have some real-time performance. Say, even though your model performs well offline, if you want to shift that on device, or if you want to, even on server, if the response time is too slow, the product team is not going to take that. They are going to, they are going to ask you to optimize that or, cut a corner. And, so always there is a trade-off between accuracy and the time response, or for robot vision, and actually there's a main difference between robot vision and computer vision. You will add some more sensors so to help relieve the task so that you relieve the burden from the model so that you add some more input or different modality so that the problem becomes easier and then you can solve that in more reasonable amount of time, right? So, but then, yeah, I certainly, in my prior life, I work on humanoid robot for Honda research for Asimo. But then at the time, we also did not work on real time. We had to cut corner for just for interaction with humans. So I had some experience with that, but but that was no fun. I mean, it was really difficult. I mean, just get a response time fast enough, and you had to do so much engineering work. So I certainly understand the challenge of that.
Yeah, in fact, I kind of see maybe Ming-Shin, you work on the Google, so you can also experience such an engineering optimization thing. But just personally, I'm doing research in this only in academia. So in academia perspective, unlike this industrial, the expert mentioned, we rather try to generalize the thing. So even if for inference speed acceleration stuff, we want to generalize. So we kind of build up either quantization or pruning approaches so that any models, if our algorithm applies, then move fast. Okay, so that is something the academia approach kind of tend to take because to us, generalization is important. But as Jungmin mentioned, yeah, thinking about the domain and then try to optimize within the domain. I think it's kind of valid idea, and I kind of learned from the industry. So, yeah, do you have any idea, Youngjun? Please, Youngjun Kim, please.
Yes, it's one of the challenging questions in the physical AI domain because I also have experience about the quantization and pruning and something else, but um, everybody wants to the general purpose technology for quantization and pruning, but one good solution for applicable for the LLM is not applicable for the VLM sometimes, and it's very hard to generalize. Yes, I believe so. And uh, in point of view, in the physical AI solutions like humanoid, we need another consideration because, as you know, the low foundation model is composed of different system level. A lot of people heard about the system 2, system 1. Nowadays, they are talking about their system 0 and system 3 because they have all different kind of time stamp scaling. So we need the millisecond, within millisecond controllability for the pose control and the safety control, and we need a few seconds to reasoning and the high level reasoning and the long horizon task. And that's why we need to design the whole process and we make it faster in the whole system. point of view. So it's very difficult question, but we're doing our best to make it make it f- make it more workable for our robot, and yeah, we still have a lot of things to do. Yeah.
I see. Yeah. Thank you. So depending on the level of the precisions and level of the task, the required is the inference time may change. Thank you for your idea and sharing your idea. Il Young Yoon, please, tell us your opinion.
Yeah, reaction time is obviously very important. But from an industrial perspective, safety is the most critical. So if a robot moves aggressively without reliable whole body sensing systems, that can become dangerous. So I think before we push robots to move faster, I think we need safe sensing systems first. Yeah? And there's also another side to latency problem, and that's the industrial ecosystem itself. My team doesn't build humanoid hardware ourselves. We purchase commercial robots and develop applications on top of them using task and motion planning. So most manufacturers don't expose their kilohertz level real-time control loop. So at the same time, it's unrealistic to expect manufacturers to implement every application-specific motions to each customer. So from an application developers point of view, our current focus is to identify tasks that can be performed safely using force-aware whole body motion planning within the interfaces that robot platforms already provide. So of course, GPU and AI models will become improve and be faster regardless. But we also need continued progress across the entire software stack, from middleware like ROS to APIs for communications to reduce latency and jitters. Thank you.
Yeah, thank you for pointing out this important issue. Instead of this speeding up, we might first think about the safety issue, because when robot moves faster, that can possibly come with the danger. Yeah, it's a good point. Okay, so then now, after this inference speed issue, we are going to move on to this fourth question. Very interesting question, by the way. It's beyond visions. So which sensor deserves the next bet? That would be my next question. I think many of these industrial experts and also I think academia, this is very interesting, a next level question. So let me start with this, Jungmin.
So I believe the sensor modality that we should focus next really depends on the target domain. So I guess the tactile sensing will obviously grow in the next few years, but in the manufacturing and heavy industry, sensors that detect force, torque, or load transfer take higher priority. So recently, there has been a trend to estimate these forces indirectly using the motor currents. Well, that might work for the lighter or service task. It doesn't really work for the heavy industry. So when we are handling like massive loads or like doing precise tasks like assembling or polishing rigid objects, this estimation introduces too much noise. So what we need is the real physical force or torque sensors. But the biggest obstacles here are system integration and cost, always. And that's exactly what's choking up the data scaling. Because these sensors are very expensive and also hard to retrofit. Very few factories deploy them at scale, and resulting in a severe shortage of the force data required for training. So I guess, yeah, instead of chasing for the higher performance, I guess the industry need to invest in lowering the unit cost and shrinking these sensors so that can be easily embedded into robot joints.
Okay, thank you for the introductions to the various factors. So, Minxing, this is a very difficult for you. I agree.
I think I will also refer to my colleague.
Right.
here.
Sorry for that. Yeah.
That's okay.
Youngjin Kim. Yeah,
Yeah.
please. I think you have a lot of idea. You already told us a little bit.
Yes. If I had to prioritize one modality, I would choose tactile sensing. Tactile sensing is very important. I believe if I had the most manipulation failure occur after contact, where vision becomes much less informative. However, I believe the biggest challenge is not the hardware. It is the data problem, how we collect the tactile sensing data from the real sensor. Unlike images, tactile signals are difficult to standardize across different robot hands and sensor technologies because there are a lot of tactile sensors technologies across the industries. And the next breakthrough will come from scalable multimodal data sets and unified sensor representations. Scaling will continue to improve high-level manipulation with the help of the vision camera data. But I believe the next scaling law in robotics, humanoid, especially post-humanoid, will come from scaling sensory motor data, capturing from humans feel and react and adapt during the physical interaction, I believe. Yeah.
Yes. Yeah. Thank you. Then I think the last, I really like to hear about this industry's idea. Yeah.
But
Yeah.
answers have already been said.
Okay.
So I would also choose tactile sensing. Of course, as Dr. Lee mentioned, the answer may depend on the target industry. I work in the process industry, manufacturing the materials like steel and battery materials, where manipulation is much more important than locomotion, I think. In our environments, robots primarily use tools or operate industrial equipments rather than handling products and parts. So that makes force interaction more critical. Even something as simple as operating a switch isn't purely a position control problem. So I think tactile sensing is the next key modality. But I would add something. The biggest challenge, I think, isn't only the lack of tactile data. It's also the lack of standardization. Different tactile sensor vendors collect data in different formats, making it very difficult to build large-scale and reusable data sets. It's certainly not an easy problem to solve, but I believe standardized tactile sensing will be one of the key enablers for scalable and unstructured manipulation.
Just thinking about one small questions to your answers. Is it possible to simulate the tactile sensing measurements, you think?
There are a lot of type of tactile sensors. So I think that is very difficult to implement at
I
this
see.
time.
Okay. So the scaling this tactile sensing sensory data is another, I think, research direction then. Okay. All right. Thank you for you guys' opinions. I think we are now at the last questions. Okay. So I think the times are a little, yeah, we are on the right time. So our final question is about this what actually triggers this inflection point. So we have discussed some multiple factors like training data, how we incorporate the physics into it, and how we can make sure that it thinks fast enough. And then in work in the real world, what kind of extra sensor we need. So among all of them, across all of them, if we choose one impactful factor that can actually change the entire physical AI moving forward. What could be that? And so pretty much what is the first priority we have to think about among all of these? So can we start with the Jungmin?
Okay. This is such a difficult question, but to accelerate the transition of physical AI from the experimental system to actually highly deployable industrial assets, I think the true inflection point will never be triggered by flashy algorithmic breakthrough or even a massive data infrastructure decisions. From an industrial standpoint, I guess the single most decisive condition is the establishment of the safety certification and standardization fused with a deterministic safety barriers. In the digital world, a glitch just means hitting the refresh button, but in physical AI, a failure means real physical damage to assets or even a threat to human lives. So we must remember that AI models are fundamentally statistical models. That means they will always have unpredictable anomalies. So therefore, I think we cannot rely on AI alone to guarantee safety. So we must integrate deterministic safety barriers into low-level architecture to instantly stop the AI if it attempts unsafe action. And more importantly, the industry has to come up with a clear and unified standardized for this hybrid system. So once we have this type of the standardized framework that mathematically guarantees and also certifies absolute safety on the shop floor, then I guess the gate will open. So that is the ultimate trigger that will move physical AI into industrial deployment.
Yeah, very good point, actually. Yeah, I missed that. But Minsheng, yeah,
Yeah,
tell us.
I think that's very good point, and this is a very difficult question. And yeah, now I think one thing close to that would probably be Waymo. I mean, the autonomous driving. It's one way, one form of physical AI, and it's getting there. It's pretty good. I don't know whether you have been on Waymo ride or, I mean, it's pretty good. But Waymo is still improving that because there's a long tail problem. There are just some very, very rare cases, and they still need to do. They cannot fail on those cases. So, and I'm sure every time you see Waymo or Tesla on news, it's because they fail in some cases, right? I mean, some real cases, corner cases, but in order to make it accessible or make it useful for everyone, then I think we still need to deal with those 0.001% or 0.0001% of cases, you know.
Thank you. So basically, the safety is the most priority, I think. Yep. The Jungmin, please, yeah, tell me your opinion. The most impactful.
Yeah, but safety is very important, but uh, we are at the early stage for developing the humanoid and the robot foundation model. And uh, I think in the classical approach, robotics approach, safety is very important, and there are lots of safety regulation about the robotics. But for the humanoid, we don't have the regulation. We are now participating in the regulation decision, some kind of uh, members for, but they are not fixed yet. They will be their job will be done until next year, but we are at the very early stage, so it is very hard to consider the safety issue at the early stages. So, and I think we need the courage to import our result to the real factory and line to collect the data from the real environment, because in the future, lot of robotics company can gather the good demonstrated data from the real environment. It's very easy problem, but collecting real data, the failure data and recovery data from the real environment is very essential for overcoming the very rare cases, because their failure impact will, as Lee mentioned, can harmful for the human and the factory gadget. So it's very, but we need, without the data, we cannot improve our model. So we are now thinking about how can we scale up the data collected from the good demonstration after we deploying the model to the real environment. We are doing our best to collect the failure data from the real environment. That's our strategy.
Okay.
Thank you.
Yeah, thank you. So data is still the important so more higher priority, I think. Youngil, can you tell us your opinion?
For me, the biggest factor is standardization. It may sound a little bit abstract, but just as ImageNet gave the deep learning community a common data set to build up and to benchmark, I think robotics also needs a similar and shared data infrastructure. In robotics, infrastructure means much more than just collecting massive data. I think we need standardized data representations that are independent of robot hardware and sensing modalities. At this time, different robots may use different sensors, but they should still be able to learn from the same underlying data representation, I think. That's why I intentionally use the word infrastructure rather than just data set. So I don't think we'll be able to build scalable level foundation models until we have a common data infrastructure with standardized representations across the robot hardware and sensing modalities.
Yeah, that is very interesting direction to research on, by the way. So even though coming from different vendor and different actual measurements, if we can connect them into this kind of common space altogether, yeah, then I think we can start to learn the more like integrated representations. Yeah, thank you for sharing your idea. So so far, I think we are done with this question, and we are about just right about the time. So if the audience have any questions, I think we can get one or two. So any questions? Oh, two, please.
Hi, everyone. I'm Daniel. Thanks so much for the talk, first of all, and to all the panelists for sharing your insights. There was one thread from this morning's keynote which I found interesting. So when we talk about large language models, we know that verification is mostly cheap when it comes to, like things like math or coding or deterministic things. And I think, Erin, you mentioned that verification in physical AI is generally a much harder problem and it's not so cheap. There was also discussion around how tactical sensing is the next most important modality. And I see how tactical sensing can help to close the verification gap to sort of make verification easier in physical AI tasks. But what's the trade-off between using tactical sensing to verify when it also mutates the environment? Because if I want to lift something to measure the weight, I also have to factor in the case that this could change the pose of the object or actually damage it or crush it. So in sort of real world use cases, what's the trade-off between using tactical sensing for verification and then also the risk that it could mutate or change the environment in the physical state?
So anyone has an idea? Like, so you were asking the trade-off in evaluation. Is that correct? If we involve this tactile, data into it, what are the possible trade-off?
Tactile sensing can also sort of mutate the environment or change the state. So do we sort of factor that into our planning or like how do
I see. Since it can change the environment as well. So I think that was the question. Anyone kind of have answers to?
We don't have good answer at that point because I'm now considering how we can evaluate the result of the tactile sensor into our real-world model for improving our reinforcement learning results. But it's very hard to detect the what's the cause of the failure. Is a failure from the tactile sensor or the force feedback? I don't know. So we can trial and error. We can make do our best to extract the our based on our prior knowledge, but I'm sorry, we don't have there yet.
Somehow I think it's open questions.
Yes, contact dynamics is much more difficult to model and simulate. And we have a lot of types of tactile sensors. Some types of sensors have hundreds by hundreds arrays, and they produce vectors, not pressure. So it's very difficult to simulate the tactile sensors in current simulators. But many researchers are interested in this kind of problems. So I expect this should be solved very soon.
Okay, and the next question, please.
Thank you for the great talk. And my question can be sort of confined to the academic question. And to incorporate those important modalities like, of course, force, torque, and tactile are important. But beyond the torque and tactile, like smell or sound, what direction can be the promising way in aspect of collecting data and architecture to incorporate those diverse multimodal data? And simulations may be very hard to accurately simulate those all modalities, and architectures also like world models, vision language action models, incorporating multimodalities seem still very challenging in nowadays. And I wonder whether panels have any insight in aspect of data and these architectures.
So the question really about like what are the data modality and possible challenges to study, right? Well, the question, yeah, I think we got the question. Yeah.
Question, but I believe the system zero is responsible for the instance instance interaction. And so by take some feedback from the object into account to change their behavior policy. And in that case, we only depends on the tactile sensing and pulse feedback without the visual processing and language processing or something, because it takes a long time to go through that kind of model. But for the system one level, we can use some visual information combined with the tactile information, and it's kind of it's a little bit tricky, but we are combining those two systems, communicate each other to solve some kind of problems. Yeah, it could be an answer or not, but we are doing in that strategy.
In a short term, I think there are likely to be some specialized robots, like to be able to smell, to be able to hear. Yes, I think.
And just to follow their answers, maybe your question is about like extra modality. If we have added to the model, then what is a promising direction to study, right? I think even right now, the MLLM, including the visual, video, sound, and then language, doesn't align very well. So if we start adding those tactiles talk, I think it will be another mess. And then we also have to think about whether they can be alignable or not. But I think it's still interesting question because we human do collaborate all sensing modality together and make a decision. So, but maybe we have to think about whether we still need alignment-based approaches to link them together. Maybe different approach. Yeah, but I think that's truly very much interesting direction to study. Okay, so thank you very much for your this questions, insightful questions, and then insightful discussions here from the panelists. I really enjoy this actually panel sessions today. I hope you guys do too. So thank you again for our audience for your participation and insightful question and discussions. And now this concludes our panel discussion. Thank you very much.